Hello.
Hello. Wait, can you hear me?
Sounds good. My mic's
There we
working
go.
then. Good.
Yeah, well, actually, yeah, it's probably a good idea for people to unmute and check their levels because yesterday we had some, volume issues. They seem to be fine.
Perfect.
Hello.
Hi, Lorenzo. You sound good as well.
Cool. Thanks.
Maybe a little loud, but overall pretty good.
Let's see.
Is it better now?
Yeah, that sounds good.
Okay, thanks.
All right. Good morning, everyone, or whatever time it is where you are. I need to flip through the opening slides before we hand over to Lorenzo. So, welcome to LPC. We would like to thank our sponsors for sponsoring the conference and making it possible. These are their names. The anti-harassment policy, please be nice. And the housekeeping rules, stay on mute if you want to speak. If you are comfortable, unmute your video as well so we can see you. If you are not comfortable, just speak. You can post the questions in the chat as well. It should be working for everybody today, hopefully. And we will be reading them out for the YouTube folks, because I'm not sure whether they can see the chat on the YouTube stream. And we would also like to thank the committee who spent a lot of their time planning this conference for us. All right, and with that, let me hand over to Lorenzo, who is working on XDP multi-buffer support. Let me give
Hello?
you the rails. Hello.
Hello, can you hear me?
Mm-hmm.
Okay, cool.
I'll make you the presenter. You should be able to switch the slides now.
Okay.
All right.
So, hi all. Thanks a lot for joining. And my name is Lorenzo Bianconi, and I work in the networking services team for Red Hat. And I will introduce here our proposed solution to extend XDP and to support jumbo frames and TSO GRO performing XDP redirect in order to overcome the limitation that we have nowadays in XDP and in particular in the memory layout. So in the first part of the presentation, I will introduce some XDP technical requirement as building blocks to explain our proposed solution, and I will introduce the main use cases for XDP multi-buffer and for or XDP nonlinear buffer, let's say. I think we can go quite fast on the first part of the presentation. So let's start. And let's say, what is XDP? XDP is or Express Data Path is a Linux kernel fast path. Actually, it is a new programmable layer that is executed before the traditional Linux networking stack. And whenever the XDP hook receives a new frame, it can read, modify, or for example, redirect the received frame. For the layer 2 and layer 3 use case, XDP can be 10 times faster with respect to the traditional Linux networking stack. So we are wondering how we can get this improvement, and we get this improvement executing the code path as early as possible. For example, just after the DMA engine has synced the received buffer, and avoiding all possible slowdown operation, in particular the SKB allocation and the SKB memory allocation and the SKB memory initialization. And XDP sacrifice, let's say, some kernel general functionalities that are not relevant in this case, but they are relevant in terms of CPU cycles. But it can still leverage on the kernel functionalities through what they are called BPF helpers. Moreover, it's important to remember that XDP tries at least to process all the frames in bulk in order to be cache friendly and to avoid as much as it can cache misses. Here in this slide, I reported what can be the XDP architecture, where we can see where the XDP hook are executed, and what is the life cycle of a buffer according to what they are called XDP verdict. In particular, if the XDP program loaded on the NIC returns XDP pass, the buffer is converted into an SKB and is forwarded to the networking stack. While, for example, if XDP drop is returned, the packet is dropped as early as possible in order to implement, for example, an anti-denial of service attack. Or XDPTX is returned if we want to bounce back the frame to the interface where it has been received, for example, to implement a load balancer. Or we can even redirect, so forward the frame, for example, to an IF XDP socket or to a remote NIC where the MDO XDPX mid pointer is executed. So, as I have anticipated, XDP can get the performance boost introducing some strict requirements, in particular for the memory layout. XDP requires that the received frame is contiguous in memory. This, for example, to satisfy the BPF direct access that is, for example, used for validating correctness. And we cannot support, let's say, an indirect layer for performance reason. So we cannot support paged frame, or we must disable jumbo frames, so frames with size bigger than a single page, whenever we load a BPF program on the NIC. Moreover, we need to reserve space in the buffer headroom for the XDP frame structure, and we will, as we will see later, we need to reserve even space in the buffer tail room for an SKB shared infrastructure that is used whenever we want to convert an XDP buffer or an XDP frame into an SKB if the program loaded on the NIC return XDP pass, since we want to run build SKB without allocating memory. Let's say last but not least, we need even to recycle RX buffers in order to get high speed. This is done, for example, through some page allocators like the time page allocator, like the page pools. So let's see what are the main use cases for the XDP multi-buffer. As I've anticipated, one of the main use cases is to enable jumbo frames, so frames with size bigger than a single page. Another possible use case is to enable GRO TSO while performing XDP redirect, so the capability to map nonlinear frames on the TX side. Another possible use case is packet header split. In other words, the capability to have the packet headers and the packet payload in two different buffers. This can be, as far as I remember, this can be used even for TCP zero copy. Or another possible use case could be to handle GRO SKB received in the VET or in the generic XDP. So, what are our constraints and what we want to do? We want, as I said, we want to support nonlinear buffers, but at the same time, we do not want to slow down the single buffer use case. We want a fast conversion from the XDP buffer, XDP frame into an SKB, and we want to continue satisfying the BPF direct access design. So in the second part of the presentation, I will introduce our proposed approach. And please note that this work is still work in progress. Last week, I posted upstream the series V14, and we are discussing about some possible improvement on some eBPF helpers that we are proposing to work with the XDP multi-buffer. So in the first part of the presentation, I will introduce XDP buffer, XDP frame, in order to explain our proposed solution. I will introduce some new eBPF helpers that we are proposing in order to work with the XDP multi-buffer. And then at the end, I will show the changes that I'm proposing, the changes that I did on the Meta driver as a reference to implement XDP multi-buffer even on other drivers. So let's see what is, let's start from XTP buffer. XTP buffer is a metadata container that is that is constructed whenever we receive a DMA frame from the DMA engine. It is important to notice that the XTP buffer is valid just in the driver NAPI context. In the XTP buffer, we have multiple pointers, for example, to the beginning of the buffer, data at start, to the beginning and to the end of the payload, data and data the end, and to, for example, in the frame size field, we have the buffer through size that, for example, for MVNet is set to 1 page. Here is important to notice that we are reserving, as I have anticipated, a space for an SKB shared infrastructure at the end of the buffer in order to run build SKB and convert the XTP buffer into an SKB without allocating memory, whenever the program loaded on the NIC return XTP pass. So here I'm reporting a XTP frame. XTP frame is another metadata container for the received buffer and is constructed from the XTP buffer whenever we want to perform XTP redirect. Because now we need something that is valid even outside of the NAPI context of the driver. So XTP decides to store the XTP frame into the buffer headroom, and using this approach introduces some constraints on XTP frame memory layout, and in particular that XTP frame must fit in a single cache line for performance reason. Similar to XTP buffer, even in XTP frame, we have a pointer to the beginning of the payload, data pointer, and multiple metadata fields, like the len field that is containing the length of the payload, the headroom field that is containing the length of the buffer headroom, or the frame size field where XTP stores the true size of the buffer from the XTP buffer. So in this slide, I reported the proposed architecture for the XTP multi-buffer. And as I've anticipated, we rely on the SKB shared infrastructure at the end of the first buffer, and in particular in the flags array available in the SKB shared infrastructure, in order to link together all the subsequent buffers, using, let's say, an architecture very similar to the one used in the nonlinear SKB. Since doing so, this architecture allows us a faster conversion from the XTP buffer, XTP frame into an SKB, since the flags array is at the same offset in both the XTP buffer and in the SKB, and running build SKB will not overwrite this field, this array. As will be clear later, we do not need to reset this flags array, but we just need to properly account the paged length of the brand new SKB. This will be clear later when I will show the implementation in the MVNet driver. So, as I have anticipated, our main goal is to implement, to support nonlinear buffers, but at the same time, we do not want to slow down the single buffer use case, that is the most common one for XTP. And to address this constraint, we added a flags capability field in XTP buffer and XTP frame. Here, for space constraint, I just reported the XTP buffer structure. And what we do is reserve the bit 0 in the XTP, in the flags capability field for the XTP multi-buffer. Whenever an XTP multi-buffer capable driver receives an XTP multi-buffer, it is supposed to set this bit, So the XTP core code can just check this bit in the flag field that is probably in the cache without the need to look into the KB shared infrastructure that is at the end of the first buffer in order to check if this is an XTP multibuffer, since probably the KB shared infrastructure will be in a different cache line. In this slide, I reported the measurement that we did in order to see the overhead introduced by our solution in the XTP core stack. And for testing, I used an Intel Xeon CPU at 2.6 GHz. And for networking, a 10 gigabit NIC from Intel run by the XGB driver. For testing, I was sending 64-byte UDP traffic through packet gen, and in particular through this script that is available in the kernel source tree. And for both BPF Next and BPF Next with applied on top our series, I ran the test for XTP pass, XTP drop, and XTP TX. We can see on the slide that the overhead is quite negligible. For example, for XTP drop, there is no difference at all, while for XTP pass is below 1%, and is roughly 1% for XTP TX. In this slide, I reported some changes that we are proposing for the XTP core stack, and in particular for the XTP network part. In the slide, I reported the XTP return frame array snappy, but similar changes have been done for XTP return frame or XTP return buffer, for example. Since whenever in the return path, we need to return to the allocator, not just the linear part of the frame, but even the fragmented part, iterating or using a proper order. In other words, before returning the pages of the fragmented part and then the linear part in order to avoid a possible use after free. So in this second part of the presentation, I will introduce some new BPF helpers or some changes that we are proposing to existing ones in order to be used with XTP multibuffer. The first new helper is BPF XTP getBuffLen that is used to compute the full size of the received frame, accounting for both the linear and the paged part. We can see on the slide that in order to get the paged length, we do not need to iterate over all possible fragments, but we can rely on a new field that is being added to the SKB shared infrastructure, that is XTP flag size, that, as we will see later, an XTP multibuffer capable driver is responsible to set whenever is constructing the XTP multibuffer. Here, I'm reporting the routine that is executed by BPF XTP adjust tail helper, and in particular, this routine is BPF XTP multibuffer adjust tail, that is executed whenever the helper runs on an XTP multibuffer. Here, for space constraint, I did not report some sanity checks, but we can see that the routine can be executed with both a positive offset, and in this case, we are going to increase the size of the latest fragment of offset, or we can run the function with a negative offset, and in this case, we are going to shrink the XTP, the multibuffer to a given values, iterating over all possible fragment in a reverse order, so starting from the latest to the first one. And whenever a page is fully consumed, let's say a fragment is fully consumed, it is returned to the allocator. we can notice that using this helper now, it is possible to reduce an XTP multi-buffer to a single buffer, to the single buffer case, to a single buffer case. And whenever we decided, for performance reason, that whenever we return a fragment, a page to the allocator, it cannot be no longer allocated. Here I reported another new helper, BPF XDP adjust data, that is probably the most interesting one, but even the most controversial one, because it is used to iterate over all possible fragments, and can be used to read or write data in the fragments. In particular, the helper set the data and data the end context pointers respectively to the specified offset and to the end of the fragment that is containing the offset. So, doing so, a caller can just use the data and data the end pointers to read or write data into a fragment. And we can see that in the slide, we take care of both the cases where the offset belongs to the first fragment, to do the linear part of the XTP multi-buffer, or if the offset is located in a given fragment. Two notes here. It is one point we are discussing upstream is that this helper in the current implementation does not take care of when the data requested by the caller are across the boundaries of the fragment, but it is up to the caller to take care of this particular case. And as it will be clear later in the following slide, but whenever the caller of the helper has, let's say, completed the management of the fragment, it is supposed to run the helper with offset 0 in order to reset the data and at the end context pointer back into the linear part of the fragment, into the linear part of the buffer, of the XTP multi-buffer, in order to continue using other eBPF helpers like BPF XTP adjust head or adjust tail that are accessing the data and data end pointers. Here in this slide, I reported a possible example of how we can use this helper. And in particular, this example is taken from the kernel self-test of BPF XTP adjust data. And we can see here that we run the helper with offset 5000. And at offset 5000, we are supposing to find the byte AA. And if so, we set this byte to BB. We can notice here that after calling the helper, we need to reload both the data the end and data pointer, similar to what we are currently doing, for example, whenever we are using BPF XTP adjust head or adjust tail. And as I anticipated, at the end of the program, let's say, we need to reset the data and data the end pointers back in the linear part of the XTP multi-buffer, running the helper BPF XTP adjust data with offset set to 0. In this slide, I reported the change we proposed for BPF XTP copy. That is the function, for example, executed by BPF perf event output helper, since before it was assuming that the memory area of the XTP frame that is working on is contiguous, while if it is running over an XTP multi-buffer, it must copy data from the linear part of the XTP of the frame received, and even it must copy data from the fragmented part. In the latest part of the presentation, I will introduce the changes that I did to MV Neta driver, as I anticipated, as a reference to an example to how we implement XTP multi-buffer even to other drivers. In particular, the main idea here is that we need to modify the driver RX nappy loop in order to process all the descriptors that belong to the same frame, building the XTP buffer, and then we need to run the the BPF program loaded on the NIC on the full buffer, so on the buffer composed by all the descriptors. For MVNeta in particular, we will need to modify MVNeta software buffer manager at the RX fragment, that is the routine executed on subsequent descriptors. And in particular, as we will see, it is supposed to set the XTP flag multibuff bit and to account the paged length of the received frame. On TX side, we will need to modify MVNeta XTP submit frame because it is executed by XTPTX and by the NDO XTP XMIT function pointer in order to map nonlinear buffers. And whenever we have addressed all the previous constraints, we can remove the limitation that we have nowadays in MVNeta XTP setup, the MTU limitation that we have nowadays in MVNeta XTP setup, loading a BPF program on the NIC. So let's start with MVNeta software buffer manager at the RX fragment. That is, as I said, this is executed on the following descriptors, on subsequent descriptors, and we can see on the slide that it is supposed to set the flags array in the SKB shared infrastructure in order to link together all the subsequent buffers belonging to the frame. And for the first fragment, it is supposed to set the XTP flag multibuff bit running XTP buff set MB, and to account the nonlinear size of the frame, of the multibuffer frame, in XTP in the new field added to the SKB shared infrastructure XTP flag size, and to account even nonlinear true size of the received frame in another field that is being added to the SKB shared infrastructure XTP flags true size. Both XTP flag size and XTP flags true size have been added to SKB shared infrastructure without increasing the size of the structure. Here I reported MVNeta software buffer manager build SKB that is executed whenever we want to convert the XTP buffer into an SKB. And as I've already said, we run build SKB on the linear part of the received frame, and we do not need to reset the flags array in the SKB shared infrastructure, since it is at the same offset in the XTP buffer and in the SKB, and is not overwritten by build SKB. So we will just need to account the paged length of the brand new SKB running XTP update SKB shared info that is reported at the bottom of the slide. And here is not reported in the slide, but I modified even XTP build SKB from frame, that is the function executed in the CPU map, and if I remember correctly, even in the vignette, in order to convert the XTP frame into an SKB. So in doing so, nowadays, even the CPU map code can convert an XTP nonlinear frame into a nonlinear SKB. Here we are considering the TX side, and in particular MVNeta XTP submit frame, that is a routine executed when we run XTPTX or the NDO XTP XMIT pointer. And in both cases, we map all the fragments that belong to the frame. For example, for XTPTX, we actually do not need to DMA map the fragments on the DMA engine, since they are already mapped there, because MVNeta runs the page pools. But we actually just need to sync them, since the MVNeta can run on not cache coherent devices. While for the NDO XTP XMIT use case, we actually need to map all the fragments of the frame on the DMA engine, since they are received from a remote NIC. Whenever we have addressed all the previous constraints, we can remove the MTU limitation that we have in the MVNeta XTP setup. That is the function executed by the NDO BPF pointers whenever we load any eBPF program on the NIC. And we can now support jumbo frames or GR OTS or performing XTP redirect on a remote NIC. For example, in the slide, it is shown in the slide that I've loaded an XTP program with ID 11 on the NIC, and at the same time, I have set the MTU to 9000. So let's see now in the very latest part of the presentation some future development that we can have in XTP for XTP multibuffer. Let's say the first development is to merge the series. It is not yet merged, but over than that, for sure, for example, nowadays we do not have any way to export the XTP driver capabilities. This would be necessary for example, whenever an XTP multibuffer capable driver is receiving an XTP multibuffer and it wants to XTP redirect the XTP multibuffer into another NIC. Or for example, we will need a wider support for XTP multibuffer, since nowadays it's supported just in MVNeta. But as far as I know, Intel folks are implementing XTP multibuffer in I40 driver, and Amazon folks are doing the same in the NEA driver. And I guess it would be interesting to implement XTP multibuffer in VirtualIONet in order to XTP redirect an XTP multibuffer to and from a VM. And for sure, we will need to work on the, let's say, on the XTP adjust data BPF helper in order to address the, let's say, the comments that we are now discussing upstream. What we are discussing upstream is to implement something similar to the SKB header pointer. Let's call it XTP multibuffer pointers, that whenever let's say the caller is trying to access data that belongs to a given, all belong to a given fragment, it can just return a direct pointer to the area. Or, for example, if the data are across the fragment boundaries, it can copy the requested data into a provided buffer. And in this case, for the write operation, we will need, let's say, an XTP multibuffer pointer flash helper or utility routine, let's say, since we should, let's say, in this case, we should, let's say, apply the changes that now are in the buffer area into the XTP multibuffer. So let's see here in the latest slide a possible future enhancement, a future development for XTP multibuffer, and this relying on the hardware scatter capability that nowadays all the hardware support. We can in some way modify an XTP in a shared, let's say, in an XTP shared frame, for example, adding or modifying headers without the needs to reallocate the memory. For example, a typical case could be set a VLAN tag sending the frame out. A typical use case probably is XTP multicast, when we have, let's say, a shared XTP multicast frame that we want to XTP redirect on multiple ports, and we want to send this frame out to each port with a given VLAN ID. For example, VLAN ID 1 on port 1 and VLAN ID 2 on port 2 in the slide, without the needs to, let's say, reallocate the memory that we are now doing in with XTP multicast. What we can do is, let's say, an idea could be to reserve a per port buffer where we can store the, let's say, the per port headers, and we can map just the shared payload with the per port buffer in order, let's say, to modify the frame without the need to reallocate in memory. So now, thanks for listening, and it's time for question. And I guess we have some times to let's say a little bit discuss about possible development of these new eBPF helpers.
Anyone wants to jump in?
Yes.
Yes, Lawrence.
Another Lawrence. Hello, Lorenzo. Thank you very
Hello.
much.
Just
Just a bit of background. I work at Cloudflare, and we have a load balancer that's written in XTP. And we also have a part that is a TC classifier. Why do I mention this? We actually had a bug in our TC classifier where we didn't take into account that you could get kind of these nonlinear frames. So my question is, if I have my XTP load balancer that I've written right now, and our hardware team decides to switch to a new network card that has XTP multi-buffer support, what do I have to do in my XTP program to make sure that it continues working? Like, the other way to ask this is like, go for it.
No, I guess, let's say, this is something that we have already discussed a bit, because yes, there are some, let's say, possible issues that can arise whenever, let's say, we are introducing these functionalities, because especially a typical example is the current eBPF all the eBPF XTP programs are computing the length of the frame, doing like the data at the end pointers minus data pointers, right? So just take into account the linear part of the data driver. So it is possible that these programs cannot work with XTP multi-buffer, but from my point of view, this is not super, let's say, severity issue, because if you just upgrade your kernel or whatever, and in the newer kernel there is the XTP multi-buffer support, nowadays for the limitation that we have in XTP, you cannot, let's say, automatically increase the MTU and when we have loaded the eBPF program, right? So just update the kernel does not trigger the issue. But if the, let's say, system administrators just modify the MTU, yes, old programs cannot work. Let's say it's not completely sure they are going to work, and we should find some way to take into account this possibility. For example, Toke has proposed a way upstream to account this, to in some way, for example, forbid the one of the two if we have loaded an eBPF program that does not support XTP multi-buffer, we do not, let's say, add the capability to increase the MTU or the other way around, let's say. But yes, the point is, I guess you should in some way touch a bit your eBPF program.
To put it in another way, it really depends on what your XTP program is doing. If it's just a load balancer that looks at, say, the packet headers, you don't have to do anything. It'll just start working with XTP multibuff. But so the only exception is that XTP multibuff changes semantics. So what it does is that you may not be seeing the whole packet. Like you will, if you just ignore the multi-buff features, you will just keep working and you will only see part of the payload. And for most things, that's just fine. But if you are, for example, counting how many bytes you're seeing on the interface, suddenly it will be off. And we had a discussion upstream, like, should we try to avoid this by having it be opt-in from the XDP program, that it will refuse to run if you don't say this is explicitly fine. But the problem with this is that, like, when you have things like XDP redirect and so on, you can't really just know from the interface. So I think we sort of tentatively agreed to just hand wave it away and say that's your own problem. If you are increasing the MTU above 1500, that's something you couldn't do before. So if you do this, you should know what you're doing and make sure that your XDP programs don't expect to see the whole payload when it's looking between data and data. And that's basically the only thing you have to make sure. And if this is not acceptable, now would be a good time to yell at us on the left.
I'm yelling now. I think, like, in terms of, there's like a 50% chance that we'll be told when the MTU is changed on our underlying network interface, I would say. So for me, that would be a hard sell to say, like, the problem with this is, for example, we look at encapsulation that is sometimes variable length, right? So we might have to look at 128 bytes. Sometimes we might have to look at 150 bytes. So it's not always clear that if you turn this new feature on and then some driver decides that the first fragment is going to be 128 bytes, it's not like there's a clear failure case where the load balancer is going to fail every time when we, do acceptance testing or something. But it's going to be something where there's a weird configuration in some edge case, and all of a sudden it goes poof. That's number one.
Yeah. So
Number
this
two
would
is,
be an issue if we see drivers or hardware that do not split at the end. Like if you have something like header splitting, right, where the first fragment only contains TCP headers, and then suddenly.
Yeah.
And I think like all of the implementations we have on the driver side is just, it's only if it does not fit in a page. So you only have a problem if your headers are more than 1500 bytes or so. So in practice,
is that something we could guarantee though from the API, or is this like up to the the driver developer to kind of promise that they won't go below that?
that would be up to the driver.
That was my question as well.
That kind of means,
and the other thing also, you mentioned header split as a use case for the multi-buffer, right? I mean, like if that would be like an explicit use case, it would probably have to be an opt-in so that existing load balancer programs like, I don't know, Catron, Unimog, or Solium and so on, that they would keep working ideally without changes or without having to be aware of the configuration underneath. Yeah.
I would expect it. So like the header split is, I don't have a concrete use case for that, but it's something people have mentioned that they might want to do. But the question is it enough that it's not something that's turned on by default, but you change it by configuring the hardware, like you do when you configure the MTU, right? That's an explicit configuration of the hardware. Is that enough, or should there be something XDP specific that the XDP program opts into?
well, for me, it would be much better if we could opt into as the XDP program writers, right? Because we know that, oh, we've dealt with this, we know how the APIs work. I think from my point of view, it would probably be fine if my program doesn't have the flag that you just, I don't know what the equivalent of linearization is, and I don't know what that means. It might be super complicated in the driver context, but as a concept, that for me, that would be much better, right? Because I know that it might be slow, but it's going to keep working for, everybody.
Maybe we can define, let's say, a given program type for this. Let's say, I don't know, XDP multibuff prog type or similar. I don't know.
The other thing I would just add is the program should always work the other way, right? Like if you add support for multi-buffer in your XDP program, it should work on a non-multi-buffer driver. So you could update all your programs preemptively, right? If you were able to do that. then it wouldn't matter when the hardware team turned it on, because everything would be working. At some point in the future, they would turn it on, and then it would keep working, right?
Yeah, so I think the scheme we had, if this were to be opt-in, was to define some kind of flag that the XTP program sets saying, I understand multi-buff. And then like either I can just ignore them, but at least it just sets a flag that says, I understand multi-buff, and the kernel will refuse to load XTP programs that don't support this if multi-buff is available on that driver, right? So like if you have an old XTP program that hasn't been updated and someone raises the MTU, so now the driver uses multi-buff, and then you try to load an XTP program that doesn't understand multi-buff, you will get an explicit failure and your XTP program will stop working. The problem is with redirect, you can redirect, say, a packet from a physical device to a VF, and the VF may not know that multi-buff is enabled. So that means we now need a global switch on the system that, like, when you have enabled multi-buff anywhere at all, the kernel will refuse all XTP programs that hasn't set the flag for all interfaces. And that's a bit cumbersome, but it would work. So
I think it wouldn't work for us. Sorry.
no.
So there's other XTP. So we write one part of XTP, and then we also have the use case I just mentioned where there's tons of network namespaces, each have a VF, and then each one of those has XTP attached to that. And so we'd have to get the other team to kind of, like, how do you do that? Like you need to get the other team to upgrade as well, I guess, or what's the idea?
But you wouldn't turn on multi-buff anywhere until you had made sure that everyone who runs an XTP program sets this flag. So, but the alternative is that you're gonna potentially see silent errors, right? So it's like there's not really any good choices here. And from an implementation point of view, obviously the easiest thing is just to say let the users deal with it, right? Which is where we're at now.
Well, I think to a degree, a little bit, I think the TC API has done that, right, for their frag thing, where you have the frag and then, or you have the linear part and then a couple of helpers. But I think in practice, it took us a while to figure out that even exists, right? So if you want people to write correct XTP, or I think we want people to write correct XTP, right, and stuff to keep working, then we should try and make it so that it's at least, you know, that's easier to get it right, is what I'm trying to say.
Yeah. I can go dig up the, I think we had some old emails where I summarized some of the options. I can go dig that up and start a new thread and make sure you're on it, and we can do another round of this and see.
That'd be cool, yeah, thank you. Also, the second API that you mentioned, which has like this kind of more SKB header pointer like, I think that, to me, that seems much nicer than the moving around where the data pointers go.
Mm-hmm.
Thank you very much for the talk.
Yes, this is something we are currently discussing, and probably at least we'll try to go along this road. Let's say.
Yeah, like this other API, like that basically came up 3 days ago or something, and there's an ongoing discussion now. So we just sort of put it into the slides like yesterday. So that will go. We'll do another round on that as well. There's some performance concern, but we'll probably end up with something like that.
Is it complicated?
Go ahead.
Oh, I was going to ask, is it complicated enough that we should add something like the BPF features flag so that the drivers and the programs can talk to each other across like which features are supported, et cetera, et cetera, et cetera, instead of having the program completely detect or just guess? Like what features the hardware and driver support?
We would like to have the feature flag thing would be awesome in any case. Yeah. That's stranded, unfortunately. I guess if someone feels like reviving that effort, please let us know.
I think when we do the redirect, we sort of need to have this feature flag when you redirect into another driver to know if it supports the multi-buffer stuff. So we have to introduce it somehow. We can introduce it without exposing it at all to user space. So I think that's acceptable as the first step. and then we'll have a fight over how we expose it to user space. But
would it be possible, like for the redirect map case at least, to, let's say, if the redirect map detects that whenever you add a device to it, that you then flag the entire map as multi-buffer needed, let's say, and then you can only ever use it in programs that expose like the capability that it supports multi-buffer, but not for others, then it would reject that it can be added to the program or so from verifier side.
This was one of the options we had with the feature thing, doing this in general for all features, right? The gnarly thing is tail calls and F replays. I assume that was why you came on, Jakub. We'll shut up now. Thank you.
Yeah, I mean, we should give John his time unless he can tell us that his presentation is short. John, you're next up.
Hello.
Thanks everybody for this
Thank
discussion.
you.
We can continue later in the chat rooms. I think this is very important work, so thanks for doing it.
Thank you. Bye-bye.
Bye.
Thank you.
Let's give John presenter.
Oh,
Oh no, wait, I need to take
I've got the
presenter.
hand now.
One sec. There you go.
Okay. Let's see. Oh, okay, and there I can click the two. All right, and I can do this too. Maybe. Oh. All right. Okay, great. So that was great. So I'm going to switch gears from the networking space a little bit here and talk about what I titled "Watching the Superpowers." So I want to spend a second just to talk about like where this talk came from. So the call for papers or call for abstracts was out in August, and we were working on there was a lot of patches flying around about the signature signing BPF programs. And so this talk is really about what I was trying to do is understand how sort of the BPF programs that I maintain could possibly work in this space. And so I actually had a couple titles that I came up with when I was working on this. And the first one was the BPF signing broke my tooling, because I couldn't see how some of my tools were going to continue to work in this signing model, where you sign the BPF object program. And I'll describe for people that aren't following the mailing list what that actually looks like. But that seemed a bit like I was just pointing out problems and not giving anybody sort of any hints on a possible solution. So I scratched that one, and then I went with the title 2 here, which was an argument for BPF runtime policy, which was I'll hints at sort of the proposal is an alternative to BPF signing is sort of deep audit control over what sort of programs are loading and how they're interacting with your system. So not simply relying on a signature at load time. And then finally, it was just kind of fun is to talk about its B's all the way down. This idea that we have BPF monitoring BPF, and then kind of where do you stop? Do you need another BPF program to monitor the monitor of the BPF programs and so on? But I settled on watching for the superpowers, so that's where we're at here. See if I can find, there we go. And then so for agenda, I want to cover kind of high level. It's going to be a pretty high level sketch. The details of how to actually sign BPF programs is pretty involved. I'll give you some links, but try to give enough detail there to just get people off the ground if they're not following the mailing list. Then I want to set up our examples. We'll use kind of a simple example here, but I think it reflects kind of the use cases that we're going after. And even though they're a little bit trivial, I think it captures the interesting aspects of signing. And then as part of those use cases, I can show kind of where I believe the tooling is going to break as you go through the signing exercise, and then sort of propose an alternative and discuss the pros and cons, what we lose from the alternative proposal, but what we also gain from it. Okay, because I think there's no silver bullet here that's going to solve all your problems. And then finally, we'll just wrap it up. So if you don't know me, I'm looking at the list here. I know most of the people here, but a lot of people, a few names I don't recognize. So I've been a kernel developer for quite a while. Been working on BPF a lot lately. Kind of also become a BPF user as part of one of the Cilium kind of core developers on Cilium project. And I am currently at Isovalent, where I work on Cilium and a lot of the other open source stuff. So that's kind of my background and where I come at this from. So I thought it was useful just to briefly discuss kind of what is the difference between kernel modules and BPF programs. So on the left, I kind of have the idea of what a kernel module is in my head. And then on the right, I talk a little bit about what BPF programs are. So this is pretty high level, but I think it's kind of interesting to level set on what the differences are between these things, because in my mind, they're not the same. Right? So on the kernel side, you have modules, and the safety depends on the diligence of the developers. Right? So you might have tooling and static checkers and all the good stuff that we have, and a lot of the testing infrastructure that we've built up. So there's a lot to help the developer there, but at the end of the day, you're dependent on the developer kind of doing good practices, right? And then it's usually built and distributed. You get your object files and you can power your distribution or from your vendor and so on. They're usually kernel version specific. So they're built against the kernel headers or a stable API in the kernel. And the expectation, I think, from many users is that they're stable APIs, right? You don't change your Netlink API from day to day. Your Netlink API isn't vendor specific. It's not like Cilium has a Netlink API that's different than anyone else's Netlink API. So they're very stable over. And the lifetime of modules is quite large. Like, I mean, you're thinking years, right? Vendor distributions are offering contracts for 5 or 10 or more years. If we contrast that to BPF, right, where the safety is built into the loading process, right? So when you load your BPF program, your expectation is that these programs can't do sort of things into the kernel that you don't want them to. They must terminate. They're not going to access out of bounds memory and so on and so forth, right? And they're often, at least in my experience, some of the more interesting use cases are often dynamic, right? So I'll have to show some examples later, but the idea being that I don't always know ahead of time what BPF programs I want to run. And there's a lot of tooling existing out there that will try to dynamically patch the programs or even just dynamically generate them based on either user input or some scripting language and so on. Kind of what enables some of that is this core idea. If you're not familiar with it, the basic idea is if I want to read a field in a structure, that field might be moving around from kernel version to kernel version. And you want a single BPF program to run from 4.19 all the way up to latest, for example. And in order to do that, we have core. The idea is that there's a BTF description of the kernel, and core lets the loader push the right offset into the structure. So you can always find your PID inside the task structure, regardless of your kernel, by using this BTF data directly. Okay, and then I think the last time which distinguishes it between BPF programs and kernel modules is the lifetime is completely different, at least in my mind in some sense here. So like you might have a BPF trace program that you use once and throw it away, right? Maybe I want to debug something on my live systems. For example, we recently had an IPsec problem. We create an IPsec debug program, distribute it, run it. Once the bug is found, throw that program out or put it in some repository in case we need it later, right? But that is not a long-living program. On the other hand, some things do have long lives, like Cilium. A lot of the Cilium programs have been around for years. Okay, so this is sort of like a high level, no surprises, I hope, for most folks here. So then I want to give a brief sketch. I apologize, this is a super quick sketch about the BPF, how BPF program signing has been proposed. And if you want all the details, the links at the bottom there, I'd recommend reading it. The cover letter does a pretty good job of describing how all this works. But I want to at least give some of the difficulties in what signing these programs entails for folks that aren't following this closely. So as I mentioned, core is going to rewrite the program. So at load time. So if you sign a BPF program up front and distribute it, that's not going to work because that signature is going to be different after the core happens, right? You don't know what these offsets are going to be, so you're doing relocations, changing the code, and it's not going to work. That signature isn't going to match anymore. So the same thing for FD, they have different file descriptors in there. You might change those. We want the signature to continue to work, right? You don't want to hard code your signature to a very specific kernel in a very specific layout, okay? And then the other thing that makes this kind of difficult in my mind is that loading BPF programs is kind of a multi-step process. It's not just a single program. It gets loaded. It has various maps, a kind of a whole set of syscalls that go into actually loading this thing up. And that's kind of what libbpf is doing, or what the Go BPF loaders are doing as well. Okay. And so what we want actually is the signature verification to capture this entire process, right? We don't want to have per kernel signatures for BPF programs. We want to sign a BPF program and have it load and match the signature across various kernels. So this has mostly, I think, been implemented. I think there's a few more things about how to get the signature and verify it. But this idea of kind of having a stable BPF program that runs across, that'll work across multiple kernels and could be signed is mostly already pushed into the kernel. The link is there at the bottom. Go and read it. But the sort of sketch here is that you build a loader program that kind of encapsulates all this information. You pass that down to the kernel, and the kernel can replay that over that loader program, and you sign the actual loader program so that way it doesn't change over time. Okay, so that's kind of a high-level sketch. So now I want to get down into the kind of what we get from signing programs. What's the advantage? Why would we want to do this at all? And for that, we'll start to talk about Alice and Eve, or Bob here. So the kind of case that I'm looking at here is that Alice and Bob are two signed BPF programs. So on the left is Alice, and on the right is Bob over here. And then we have this malicious Eve who wants to eavesdrop on the kernel, or maybe Alice's maps, for example, right? So if Alice.o is signed and Bob.o is signed, and then Eve.o doesn't have a key, then trying to load Eve.o there is going to get rejected by the signature checking in the kernel, right? And this is what we want. So that's a good win for signature checking, right? And then I just note here is as long as you get your file system correct, if Eve as an application is trying to read other maps in the system, and you shouldn't have access to those maps based on permissions in the file system. So you've sort of isolated Eve here. Eve can't inject programs, and Alice and Bob are happy and running correctly because their programs are signed. Okay, so that's sort of the immediate win from signing. And then what I want to talk about next would be what I'm calling imposter Alice. So we captured the obvious case with some arbitrary application trying to load a program that's not signed. Okay. The next one is this imposter Alice. And so what I'm saying here is that something application or daemon or something in your system, it looks like Alice, it behaves like Alice, except for it tries to load a program that's not Alice's.o. And again, because of signing, when Alice tries to load that corrupted Alice.o file, it will be rejected because the signature won't match. Okay, so this is good. This is what we want. But there's a kind of a small kind of hitch to this whole process here that I want to call out here. So if Alice is not kind of a corrupted or malicious program, but is instead generating dynamic BPF programs, imagine like an XDP filter or TCP filter, a runtime generated network program, or something, like your BCC tracing hooks, how can those don't look signed from the kernel side, right? Because the programs are changing. It's not clear to me how signing can solve this case. And so what happens is that Alice with the dynamic program generation looks like the Alice that's been corrupted, okay? And so the signature is then going to reject Alice.o even though there's nothing particularly wrong with Alice, maybe we want to run BCC tracing hooks for debugging or otherwise, but we just can't do it here in the signature model because there's no way to sign Alice.io unless you give Alice the keys, of course. But we don't really want the keys sitting on the system, right? And so this highlights the cost of signing, is how I'm referring to this, right? So you get these good properties where Eve can't load and corrupted Alice can't load. But what you're doing is you're saying that dynamic code generation, dynamic optimizations are not going to be distinguishable between a malicious Alice and what I'm calling a good Alice, or your dynamic program generation, right? So this is the cost. So we get the goodness, but we also lose this dynamic programmability. And then what I wanted to say is that, like, it's not like you're this is some hypothetical case that doesn't exist. There's lots of reasons you might want to write dynamic programs, and there's lots of tooling out there today that actually that will break when this happens, right? So this is why I started thinking about the problem is, for example, BPF Trace is a high-level language. You can generate the BPF program from the scripting language, for example, right? P4 is another one I've worked on in the past. You define a DSL with your networking, and then you'll generate your BPF programs and distribute those as sort of networking blocks, right? And so you can optimize your networking stack for exactly what your networking requirements are. Cilium, which I work on, also does some optimizations of the BPF layer. So you'll have a pod-specific BPF program that's optimized for that pod. This allows you to do things like skip MAC checks and IP checks and various other things, and just optimize for the features that are enabled on that specific pod, right? And also inside the Cilium kind of umbrella of tooling, there's a PCAP recorder, which has an XTP basis, right? So it's not clear how these would easily work inside the signing framework, because if you sign the program, well, the program then can't modify the BPF, okay? So again, we get some goodness in that we can't load this corrupted program, but we've broken at least these tools. Okay. So that was kind of the first title, right? BPF signing broke my tooling. And so now we'll kind of go on to the second part here, which is how do I go about fixing this, right? So what I want to achieve is I want to block the malicious actors, Eve, in this case, from manipulating programs. And I also want to block sort of Alice that I don't expect to be generating optimized code, but I want to allow the code generation. And so the next slides here, I'm going to go over kind of a proposal for that and kind of what we gain and what we lose. So first example, the one we already covered, we want to ensure Eve cannot load the programs or read or write to maps. So that will be our first example that we'll show with the proposal. The second example, which we didn't talk about before, but we want to ensure that if we do have a corrupted Alice, that it can't, that it stays contained, right? So we talked about if a program tries to read a map from user space, we can have file systems protected. But then there's a question about what happens if the program is a BPF program. How does we protect the maps and so on from that side? And also, it was really interesting to look at this from the perspective of least privilege when you're talking about maps. It might be perfectly fine for Alice to read a map that's been published by Bob, but we don't want Alice to say write to that map. And that can be either because Alice is malicious, or perhaps it's just BPF tool and somebody mistyped a key and they delete your firewall. You want to make sure that sort of permission-wise that's not allowed, but you still want the observability piece from the debugging. You want to be able to read those maps, etc. So we want to get that supported. And then the last piece, which we talked about, is this dynamic code generation. We want to make sure that Alice still works even when Alice is dynamically generated, but we want to try to minimize the impact that we are causing here, right? We want to make sure that we have some ways to ensure that Alice is a valid program that should be running and should be generating these programs. Okay, so those are the three examples we'll try to solve. And then let's talk about the tooling that we have to do this. So, I used a handfuls here. FS Verity, which is a read-only file-based authentication protection. It's in the kernel. You can read about it. I got the link. The basic premise, I'll show kind of on the next slide on how that works. I assume you could also use IMA for this, the integrity measurement architecture. I didn't do that in this in these examples, but my understanding from reading the documentation is that would be an alternative to FS Verity. And then, of course, we have the BPF Cilium and our superpowered BPF. Okay. All right. So what is FS Verity? In case you don't know, there's a couple kernel fields you enable. So you can enable config Verity. And then you have this user space component, and you mark your file system with support for it. And then you can start signing your files in user space. And then any reads of corrupted data will fail. So if you do something like DD over the top of it with some random data, then the next time you try to open it, it's going to fail. They'll open. Okay. It also has keyring support. I didn't poke too much into that yet. But then that idea is, instead of verifying the signature, just reading the signature, like as an audit support, you could put those signatures inside the key ring in the kernel and use that, which would be in many ways more secure, right? And so on the right here is just sort of a dummy example. Is you have your Alice, you corrupt Alice, and then Alice won't launch, which is what we want. Okay, so what is that? So what does that look like from the BPF side? Is how do we read these out of these hash values out of the file system, right? So the first way is we could do it from user space with ioctl. We don't really want to do that because of the TalkTow issues, right? If you launch something, you read its hash from user space based on some event, like we exec Alice. You could then, in theory, stop Alice with the kill all or something, but Alice may have already loaded the program or gained kind of access to whatever secrets it was trying to get. So we'll just kind of cross that off and just mention it for completeness. What's interesting is that it's quite trivial to access it directly. There's this SMP load acquire from the inode to the iVerify info, which has a memory barrier. So in my examples here, I sort of skipped the memory barrier, but there's work to do memory barriers, and I think it's included. I have to double check what kernel version it was actually added, but for a production version, you'd want to make sure you have the correct memory barriers there. But inside that structure, you have your root hash and your file digest hash, and the file digest hash is the one we're interested in here, which is a hash specific for that file. So the workflow then is when you exec Alice, you can get the inode, and from the inode, you can get the hash, and then you can decide if that's a valid hash or not, and a bit about what that means to decide if it's a valid hash. And then finally, there's a question. I had a few open questions and talk about at the end is whether there should be a helper. If we need a helper to actually instantiate the hash rather than have user space do it, and what the kind of right control plane would be for such a thing. But before we do that, I just want to show that this solves kind of some of our solutions to our examples. So the first one that the signature solving solved, and probably the easiest one, is that you have this malicious Eve who's trying to eavesdrop on the kernel. They try to load their program with eve.o, and the signature failed at the load time, right? But if we, for example, didn't have signature loading, could we still stop this with kind of a file verification approach? And the answer here is yes, we can. So instead of stopping at this BPF load time, we did kind of a different process that we verify Alice and Bob at open that they're allowed to load BPF programs, and then when Eve launches, we say, well, this hash is not supported in my list of supported hashes that can load BPF programs. And so we, when Alice tries to load, we go, that's a Alice task struct has been annotated with the correct annotation to allow it to load BPF programs. whereas Eve has not. So we'll just stop the loading of sys BPF load. Okay, and we wrote a little tool for this, and the tool I called Watch BPF. It's just a cobbled together set of scripts, but I think it illustrates kind of what a flow would look like when you do this. And we have a small configuration file, which we put the allowed hashes in this case. And we'll talk about how to do this better at the end, I think, if people are interested. So the first thing we see, as I mentioned, is you see process Eve startup. We attach to that task struct, after looking at the hash, we attach this BPF denied attribute, which is just part of the metadata now that flows around with this task struct. And then when Eve tries to load a program, we return denied. And so we don't allow it to load. I added a few kernel patches to make this actually work, but you could do it with LSM, I believe. I'm still kind of fleshing out the details to make that happen, but I added a new action that would let it return an ePerm error directly from kprobes. So that's there, and it does what we want. And then we see this Alice process, it gets launched. And then what's interesting about this is because it's just a BPF policy and it's implemented in your own policy BPF program, you can just do kind of all sorts of interesting things that aren't just allow and deny. And so we added a prog approve and a maps denied. This is perhaps a bit silly, but it sort of illustrates this ability to add kind of fine-grained policy. And what this means in our kind of mock program here is that Alice is allowed to load BPF programs, but Alice is not allowed to use maps. Okay. Again, maybe a bit silly, but you could imagine more fine-grained, like read-only maps are allowed, or is not allowed to update certain maps and so on. And then what happens here is when the sys BPF call is made to load the program, we get the task struct, we go back and we get the attributes that we associated with it from the exec, and we say, okay, we have the right bit set here, we can approve the loading of this program, and this allows Alice to load the program. And then you can do other things. At the bottom here was just I was continuing to play a few games with this sort of policy engine. You can say, if the user space application Eve ever tried to update a map by calling a syscall sys BPF update, we could just deny it because it doesn't have privileges to use sys BPF update call. Right? And you can get these when you look at a sys BPF call. You can pull this out of the BPF attribute strats, just using your normal kind of core syntax for that. Okay, so I think what we've shown is that for this first case with the very obvious malicious program Eve trying to eavesdrop on the system, it's pretty trivial to block the load without even using BPF signatures at all. Right? You base your attributes based on the application that's trying to load the program and its very specific hash that it has from either your FS Verity or IMA or sort of any of the other hashing schemes that you can think of, as long as you can get at it from the BPF side. And I used FS Verity because it was inside the inode struct and quite easy to pull out. Then we also showed that you can do things like read-only map policies or read-write map policy. And here we just have a blanket deny policy, but we could quite easily do even more fine-grained policies. We're only allowed to update, only allowed to read, only allowed to update certain types of maps, and so on. Right? Maybe never allow Alice to manipulate the tail call maps, for example, because we know that that's a way to get programs to be skipped and so on. So those were the two, I think, easier cases, and I hope I've showed that they're not signature checking on the BPF objects isn't really required to kind of catch those cases. But there's this third case that we talked about where Alice is corrupted at runtime. So in this case, what happens from kind of my watch BPF demo here is that you Alice gets launched, the signature checks out at launch time, but as something kind of after that, Alice is corrupted. Right? And once that happens, now the question is that metadata that's associated with the task struct hasn't changed. When Alice loads that program, what is going to happen is Alice is going to get approved to load the program. Okay, so this is both bad. So it means that if Alice is dynamically generating correct programs, everything is good. Alice can load their programs. But on the other hand, if Alice is generating malicious programs because the program's been corrupted from some other kind of malicious user, now we have an issue where what previously would have been caught by signing is no longer caught. Right, so we've got the good. We can now do dynamic programs with some confidence that what we started with when we launched Alice was good, but we've kind of removed the ability to detect this kind of runtime corruption case for Alice. So, what are some things that we might consider doing? Oh, sorry, I skipped a slide and I mentioned it there. Was that we talked about what's the thought experiment? What could Alice do even if we had signing is kind of the point of this this slide. And what I wanted to point out that, and just to ensure that folks aren't putting too much, putting too much kind of emphasis on the signing, is that BPF signing is going to ensure that your BPF program is correct, but it says nothing about your user space side, right? And as a thought experiment, what can your user space side actually do? If you have like a Cilium, like a networking application there, or a load balancer or whatever, there's kind of lots of things the user space could do to break that application. Besides, even if the sign program was loaded, they delete the firewall, redirect all traffic out of different ports, eavesdrop traffic, etc. So the same way with observability programs or security applications that are using LSM and stuff. Maybe move attach points around or modify tail call links to sort of change up the program. So the point I just wanted to be here is to be careful that you don't decide that because your programs are signed, your programs will do the correct thing that they were signed to do. All we're saying is that the program that's loaded in the BPF logic containing that program has been signed. But that doesn't mean the logic from the user space side is going to do the correct thing, right? So just to be clear that even though you have the signed program, you can still get very negative effects, right? Perhaps not as bad as if the BPF program was directly manipulated, but still, if this is critical infrastructure, this is your load balancer, you're still in a whole lot of trouble if the firewall is deleted. Okay. And so as an alternative to signing, or maybe as a complement, depending on where you stand on signing your BPF programs, so what could we do for these to detect runtime corruption versus dynamically generated programs? And so I have a few ideas. These are just proposals. They're not something that I implemented in that sort of sample program that was dumping these fields and adding, approving or denying the launching of programs. They're just thoughts. The basic high-level thought here is that if we had enough information about the program being loaded, can we create policies that are good enough to allow dynamically generated programs safely in these environments that really want to kind of clamp down on what their programs are doing? Or sort of alternatively, if it's an auditing environment, you can say, well, that's quite odd that my Alice program, for example, has, for the last 6 months been running without a write user call at all, and then all of a sudden starts to write user data, right? That might be something that your audit team should go and investigate, for example, right? And so what kind of signatures are interesting from a BPF side? We have calls, so you might be interested in any types of helper calls or what the CFG is of the program. If a program that was a networking program wasn't reading kernel memory and starts to do a bunch of probe reads, that might be an interesting indicator of the type of program that was generated. Map reads, map writes, we could do enforcement on to ensure that your BPF tool program doesn't get locked out by, or your BPF trace program doesn't get locked out by signing. It's still allowed to load, but perhaps we don't ever allow it to, for example, write to maps. It's just a debugging program. It shouldn't be allowed to write to any of these fields. And that might have just operator value, for example, right? You don't want to be debugging a system and then accidentally delete a map entry. And so there's kind of all these things that we could consider including, and there's really how would we get them? The thought that came to mind recently is that we have these attributes now in an LLVM that were recently added that can be passed down. It seems like one possible avenue to do this type of BPF program behavior modeling and policy would be to include from LLVM side a list of all the sort of helper calls it uses, all the map operations, so on and so forth, figure out the right set of attributes you want to associate with that's valuable from a BPF policy side. And then have the verifier ensure that only those helper calls are used, for example, right? And then the BPF program you're having could read a kind of a bitmap of BPF calls. Your verifier is going to ensure that kind of type definition of the BPF program is honored. And this would give you the kind of ability to ensure certain calls are used, or insert, update is never used, or delete is never used, for example. And so I think what the sort of summary here, sorry, I jumped ahead again. I'll give you one more open question list. But what I was going to say is I think the summary of sort of this idea here is that we want to make sure our dynamic programs keep working. And in order to do that, it doesn't appear that signing is a correct solution for that. So we at least need to sort of either only do signing when we know the programs are not going to change, but allow unsigned programs if they meet sort of policy guidelines. Is the proposal here, versus if you don't have that flexibility, you're going to get into a case where your BPF trace tooling doesn't work, your debugging tooling doesn't work, just because that is all dynamically generated code. Then if we went this route, the next question I have is some open questions. What does verify mean, and what does authorize mean? And what I mean by that is, in my sort of example program here, what I did when I verified them is I just looked them up on looked up the hashes in a map and was like, those hashes match. So we should be good to load this program. This is sort of perhaps not as secure, for example, as having key rings. But in order to get into the key ring, we need to think about, how does a BPF program have the ability to read the key ring in a way that's secure? And then the next question is like, how do we know that we should authorize it? Do we need to have read-only maps? If we, like, how do we secure that authorization policy from being modified by, again, the same tooling you're trying to allow, from BPF tool side or BPF trace side? So kind of what are the next steps for this thought experiment on my side? I've been thinking about, what does the control plane look like? How do we use the key ring? Instead of having the file system kind of pre-configured, how do we trigger these measurements from the file system's BPF side, right? You open the program, maybe it's not signed. Well, we should generate a trigger to do the signing, right? And we have this on the IMA side as well already. There's an IMA hash, but it's only usable from LSM. So the question is there kind of more flexibility that could be gained there? These are all things that I've kind of been thinking about as I did this work. So in summary, I think hopefully I've hammered it home enough already, but BPF program signing appears to be incompatible with much of the useful BPF tooling. BPF traces, you're debugging these kind of really interesting use cases. Application signing covers many of the obvious cases, right? Like if the application is allowed to load programs, you get 2 or 3 of those examples covered, right? The next point I just wanted to make and reiterate was, like, even if your BPF programs are signed, corrupt application can still break your critical infrastructure. And finally, I think improving visibility into BPF program launch allows this ability to audit and dynamically build these policies. for these dynamic programs as an alternative to BPF program signing. Okay, and with that, I will stop. So thank you, and take any questions.
Thank you, John. There's one in the chat if you can take a look at that.
Okay. Let's see. For the userland changes within our maps and program logic, for now we're detecting if security BPF map gets FTD followed with a probe for the maps we're currently manipulating and tainting the execution, saying it was compromised. Yeah, so I think that's the kind of thing that we've been looking at doing those types of operations. And I think what we're just proposing here is maybe even more fine-grained is useful, right? Not just map get FD, but maybe map get FD should mark the task as read-only, because I don't want my debugging tools to ever write to my firewall maps that are managed. So, thanks.
John, thank you for your talk. I think to me it sounds really nice. I could see that we would use this for the DDoS protection that we have, which is also like a code generator, so we can rely on that very much. I think it would be nice. So like one comment why I think it would be nice for us, I think the infrastructure to do signing would be provided by another team. And I've spoken to somebody a while ago, and I think the idea would be that we kind of authorize binaries that have been built by our CI infrastructure, which we kind of trust. Right. And then we could just take this, we want to do this for other binaries like our Nginxes, etc. We could take that and apply that same idea if it works. We could apply that to BPF. So I think that's really nice. I have a couple of questions, and one of them is how would this work with dynamic libraries? I guess that's kind of the obvious problem. And then the other one is how, or maybe this is kind of depends on implementation, I'm not sure. How would you kind of attach signatures or distribute signatures in this model?
Right. Yeah. So I think the dynamic library one is perhaps easier. So if you have a dynamic library that's also signed by IMA or FS Verity, then presumably if that library has ever been manipulated or corrupted or just is the wrong library, for example, right, then the signature shouldn't match on the open of the library. So there's two ways I think that could work. Either you could just rely on the normal file system signature checking to fail to load because it doesn't match. Or you could just use kind of the BPF side on open. So when you open the shared library, put a kprobe hook, read it. If it doesn't match the signature, do whatever, right? Maybe it's just the wrong version of the library and it's not terrible, or maybe for some reason that library has been corrupted, or it's there's hundreds of reasons on why that might happen, right? So I think that can be solved kind of that way. I haven't actually gone through the exercise of trying it, so like there's still that the theory to practice to see how what happens. And then the other question was about attaching something. Sorry, I lost the last question.
Like how will we distribute these signatures? Is it something that's kind of baked into the ELF, or we ship it as an extra file, or is there tooling?
Yeah, so that was the open question I had as well. So right now for the kind of little scripts and things, right? I just encoded it into the ELF, right? They're just there. We check them. That's probably not going to work for your CI example, for example, right? You don't want your tooling to somehow encode the correct hashes back into the ELF and then rebuild it. It just, I don't see how that could possibly scale, right? Yeah, I think it's a good question. I'm not sure exactly how that should work, and I think it's a good kind of next steps to understand. One thing I would look at is like how do the existing file systems manage these signatures for their key rings? And I'm coming at it from the BPF kind of networking side as someone who has all these tooling that is auto-generated. Hopefully, like we can find somebody from the keyring side who understands how that keyring side is distributed kind of above the kernel. Maybe leverage some of that, but it's just a work in progress. Cool. Any other questions?
Hi, John. So this is Alex. Nice presentation. Thank you so much for putting together all the slides on and the thoughts. I really like the idea. I think it has a lot of potential, and beyond from what you mentioned of providing a more secure signatures and more flexible, I think it will resolve all of our ongoing fight with unprivileged BPF as well, because of all the spectrum meltdown and all the exploits that coins. Well, they're not really exploiting BPF, but they're finding new ways of doing speculative execution in the CPU. So if we have this more flexible BPF-based way of writing the policies through the as a BPF program while using a severity mechanism for the signatures of the binaries, included like shared libraries and all the collateral, as I said, that should work. I think it should solve all of this issues with the unprivileged, including this signature verification of dynamically generated programs like BPF Trace. So, and it sounds to me is that the biggest here is, and probably actually have, like as you said, there is AMA hash access from BPF side already. There are LSM hook in the right places, like this BinPRM exec. So like all the shared libraries, like at this point, the programs with LSM probably we just need to have an access to severity metadata to check for the validity of the binaries and shared and etc. And it should all just work. I think like it seems to me that to make this dream achieved, it's more of the tooling work, more of the user space work, more of this watch BPF making it like production ready than changing the kernel.
Yeah, I mean, I agree. It's like I didn't put a ton of time into this watch BPF, right? Like this was just like a proof of concept that, was done in a couple of days. So it's not, there's definitely a lot of work to go from that to something production. But as a BPF infrastructure side, I think it's mostly there, right? You need maybe a couple helpers. I just grabbed it, landed in there as quick hacks, and that was about it. So
yeah,
I think it's
absolutely. The access to severity is like really nice, and it will probably go beyond just signed BPF programs, but to the rest, right? So
yeah, I think so. There's also some root signing stuff too that is sort of outside of my knowledge, but I could imagine also being useful. But that's sort of I think a to-do, or somebody who's really familiar with how all the keyring stuff works could maybe say something about that.
I also like the idea of adding, I think in one of the slides you mentioned to have another hook, like LSM like hook after the verification, when verifier already like collected all the data about the programs, like what helpers it used, like everything. In this case, we don't even need realistically LLVM annotations, just a hook after verification all completed and all the data is gathered. It would be nice. Like in some cases, we can use that as part of the lifting some of the limits, for example, like this 1 billion instruction limit, that could be part of this decision making, like whether a particular user is allowed to use only 4,000 instruction, another user allowed to use 1 million or 1 billion.
Right.
Would be interesting, whether certain kinds of loops are allowed, etc., etc.
Yeah, I mean, even just a bitmap of the calls, right? The helper calls. Some like we recently disabled user write, for example, right?
Yep.
And a lot of like maybe 99% of the cases that's the right decision, but there's maybe one case out there that you want that to be okay, and having a bitmap is something the verifier should be able to do trivially. I mean, just collect them as it's going. And BPF policy, then it's sort of on you to decide what you think is valid. So
yeah, exactly. Yeah, it will allow like any kind of, because after verification we'll see what kind of maps it's using, all helpers. We can allow or deny any combinations.
I carped on the read only one a little bit, just because like I deleted something from a map with my debug the other day, right, on accident. And I was on the wrong node, right? But if that node was sort of had something like this, maybe BPF tool wouldn't be is allowed to read but not write these maps, because I really don't want to accidentally delete something from my firewall, So even simple things like that.
All right. Thanks again, John. Great presentation.
Thank you.
Let's We're running without breaks. I hope that's okay for everybody. Next, we have Dave. Let me give you a presenter, Dave. There you go. All ready? Take it away.
Yeah, I think so. Well, Alessandro, are you here? Awesome.
Yeah. Hello, everyone.
Perfect. All right. So our talk is about improving the eBPF developer experience with some Rust. So before we get started, just a little bit about ourselves. I'm Dave. I'm a software engineer at Red Hat. I'm not a kernel developer. I've been working on system software in Go for about the last 7 years, a lot around networking and containers. And I'm particularly excited about eBPF as it allows me to kind of step further down and get more of the kernel goodness, but still maintaining some guardrails. And that's probably one of the things which I've enjoyed most about working in a higher level language, is the amount of guardrails that are there for developers in terms of all of the static analysis tools and various other bits and pieces. And it's a very comfortable environment to work in. So really, my motivation for this talk and the work that I've been doing is trying to allow developers to succeed with eBPF as much as possible.
Cool. Hello, everyone. I am Alessandro. I work at DeepFence, where we use eBPF for both network analysis and observability. I have been sort of working in the last couple of years in trying to make using eBPF from Rust first class. I added support for eBPF to the Rust compiler, and then earlier this year I started AYA, which is a new eBPF library that we're going to talk about in this talk.
Okay, so one of the key things about this talk is developer experience. So I'm just going to define what we mean about by that first before we dig into some of the more technical details. So my path into eBPF, which feels fairly typical for most people new to the space, is you read a blog post from Brendan Gregg and your mind explodes with possibilities of things that you can do with BPF Trace and one-liners in perf, and you get really, really excited. Then you find a problem which requires more than one line of code, and at which point you have to choose your own adventure, which really does feel like you're walking off the edge of the map and here be dragons, because the space is very wide and there are a lot of options for you to be able to get started with eBPF, from DSLs like BPF Trace and System Tap through to writing code in C, and then your user space in another language, libbpf, BCC. There is a whole ecosystem out there, but it's not particularly well documented. Best practice is evolving very quickly. And for me, as this systems developer that's used to having all of this great tooling supporting them, what I want is to be able to get moving as quickly as possible so that I don't lose that momentum from having that great idea to kind of getting lost somewhere and not being able to make any progress. So the kind of 4 tenets of developer experience that I'm interested in are documentation. So before I embark on my project, I want to find out as much as possible about the space that I'm entering, learn what type of program types I'm going to need, understand which map types there are and how I'm going to use those. And at the moment, because the space evolves so quickly, documentation is fragmented. Facebook's blog, for example, fantastic. Oracle has some good documentation, but there is no central place to find that. And unfortunately, search engines are against us here, because when you Google something for eBPF, what you'll end up with is a blog post which is 4 years old as being, advertised as current best practice, which, as we all know, there's things like BTF which have been recently added, which have changed things, and we're still ending up following old practices and undermining the progress that we're going to make from the very get-go. Once I've read some documentation, I want to get a development environment spun up as quickly as possible so that I can get my program bootstrapped. Once I've got that environment, then I'm interested in how quickly I can build and test and troubleshoot. I'll write some code, I'll run it. Does it do the thing I want it to? No, okay. And then I will carry on doing that until I've kind of exhausted myself and got to a point where my application is working, or at least I think it is. And then finally, I need some tools for debugging. And that can be anything from logging to, at the moment, in most of the examples, it's printk. That's the state of the art, effectively, as far as I can tell from documentation, which isn't great, unfortunately. So given the developer experience was a little bit rough from the stuff that I did, I was really interested in what approaches there could be to have a slightly better experience, something turnkey, where I can stay inside one environment with one tool chain, one language, and be able to kind of work in there as quickly as possible. And it seems that Rust is a pretty good choice. So Alessandro, why don't you tell us a little more about why Rust is a good choice for this?
Yeah, but first I'm going to say, just so everyone knows, I actually love C. I have been running C essentially my entire career. What is great about C is that it's simple, it's minimal, and it does the job. And maybe surprisingly, I think that's also what I like about Rust. Rust is very expressive, but in a way, it's also very simple for some definition of simple. You can, if you want, you can essentially use it as a glorified C. It does not have a garbage collector. It does not have any kind of runtime or anything that gets in the way. You can use it as C with a more powerful type system, and also really powerful macros that are way more powerful than the C preprocessor. And probably, and most importantly, what's best about Rust is all the tooling that comes with it. From Rust App, which is the tool that you use to install Rust, and including the eBPF cross compiler for Rust, to Cargo, the package manager, to third-party tools. From starting to building to publishing a Rust project is extremely easy. Next slide. Yeah, so Aya, why did I start Aya? First of all, with Aya, I wanted to create something that was easy to use and also very easy to deploy. I started working with eBPF with BCC, and BCC is great. And if you use it with Python and with the little DSL with the Clang plugin, it's fairly easy to use, but it's not very easy to deploy. It requires headers, and it requires a bunch of shared libraries at runtime. It's just not a very nice experience to deploy. So one of the goals with Aya from the get-go was that I want to create something that would be extremely easy to compile as a essentially self-hosted binary that contained both the user space and the eBPF code. And yeah, I think we actually managed to do that. It's the early days, but I think we're there. So what is Aya exactly? It's not one but two libraries. It's a user space library, very similar to libpf, but for Rust and written entirely in Rust. It does not use libBPF. It's a complete new implementation, and this obviously has pros and cons. The biggest con is that libBPF is actually great, and it implements a lot of features. So by not using it, we're going to have to re-implement all of those, which is not an easy task. But I think that the pros are worth it. AYA today does not depend on any external code. It does not link to any external libraries. On my laptop, the whole project builds in less than 10 seconds. Yeah, it doesn't even require kernel headers because most of the bindings are pre-generated, and the ones that cannot be pre-generated, we have tools to generate them. And it's a new project, but it already implements most of the map and program types exported by eBPF. It implements BTF, core relocations, function call relocations, and more. It's a new project, but there's already a lot of features there. And then, as I said, there is also an eBPF side, which is an actual library that you can call from eBPF code. That part is definitely more experimental. It's something that we are still playing with to kind of understand what kind of API we want to provide. But what it is today is it's essentially a high-level and type-safe API for maps and for helpers. And yeah, as we've been saying, ease of use is one of the main goals of the whole project. And now Dave is going to show you some really cool stuff that he's been working on to that extent.
Yeah, so with this idealized developer experience in mind, what I wanted to do was to kind of see how far I could get with AYA, which was where my research led me as being a good place to start. So what we do have is some documentation. It's a good place to start. We have a book which runs through a very simple example of how to create an XDP program. And it's fully turnkey, all inside one programming language, with a lot of helpers and guardrails, which I'll kind of go into in a moment. Not only that, one of the nice things about Rust is that we have wonderful API documentation as well, which is auto-generated for crates and hosted up on docs.rs. So when a crate is published, we have API documentation, which we can kind of click through and read. So as a developer, I've got my book and I've got my API documentation, and this is a fairly reasonable place to start. The book we're hoping to expand to kind of cover more use cases and examples from things from the community, like the various tips that we found working with trace points and various pieces. On the second piece for Program Bootstrap, we're using a tool called Cargo Generate. So you can type this into a terminal. You'll get prompted for a project name. Choose what you like, and then you can select from a certain type of eBPF program that you're planning to write. Once you've entered all of this in, you will end up with a skeleton project which is put in place, which covers the build system. So not only can you have cargo one command to build, it will generate also the ability to share code. So let me just show you the project structure. So you run that command, you end up with one module, which is for your user space application, which you can write in Rust and take advantage of things like async and all of those fun things. You end up with a common package, which allows you to not only share structure definitions, but also code between your user space application and the eBPF side of the application. And then finally, you get a eBPF module as well, which is where your eBPF program lives. So all of this, all in Rust. One of the things that you will find as you journey through eBPF is that you're going to need bindings to, or you're going to need a Rust binding to something which is in the kernel. And we actually have a tool to do that called AYA Gen. So you can run this and generate a Rust binding to all of everything inside the VM Linux BTF type definitions, or just specifically the bits that you need inside the program. And that, again, is all in place for you and covered in the documentation. And then from the build and test loop, it's a case of running 3 commands: 1 to build your user space, 1 to build the kernel application, and then 1 to actually run your application. There is an error on this slide, so don't follow this. Follow the book. We have to actually run using sudo here because we need permissions to load BPF programs, which you don't have as an unprivileged user, thank goodness. We're using nightly Rust to build our eBPF program here because we need features that are only available currently in nightly, but eventually, once as the Rust ecosystem matures and the features we need move into stable, this could plausibly be 1 command as well. All right, Alessandro, do you want to talk about debugging?
Yeah. So my experience debugging eBPF is that, say that you write your code and it compiles and it even loads, but it doesn't behave the way you expect it to behave. What you do is you start adding BPF trace print K calls everywhere to kind of try and trace the flow of the program and find your bug, if there's a bug. And then say you fix it and you have to go back and remove all the print Ks because they're slow and sometimes they allocate stack space. So essentially you want to remove them. You don't want to actually have them in your production code. When in cases in which, say, you need to dump some data that is not supported by the formatting of BPF trace print K, what you can do is you create some ad hoc perf event arrays, you dump the data you want to dump to inspect to a map, you output it to a map, and then you write some user space code to extract it and print it or inspect it or do whatever to understand why your code is not working. That all can be done, and I've been doing it for a long time, but it's pretty inconvenient. Next slide. One thing we provide with Area, it's a separate library for logging. This is not part of the main library, so you only get it if you only need to compile it if you want it. But it's essentially an implementation of the Rust logging system for eBPF. So it supports different logging levels. It supports string formatting. It supports the formatting is generic actually. You can also implement your own formatting for your own data types. Yeah, this what you see on the screen is essentially the whole API. A nice thing about this API is that you can actually leave all these logs in your code, and then at compile time, you can decide which levels are enabled. And when you do your final release build, you essentially say, I do not want any levels enabled, so that the logging macros expand to nothing, and it's essentially like if the code wasn't there. Next slide. And yeah, IAlog as well comes with both eBPF and a user space side. This is what the user space side looks like. Well, the user space side is one function call that you call, and it will automatically fetch the logs produced by the BPF side. It will route them through the standard Rust logging system, and this is what you will get on screen. A nice thing you can see here is that you actually get the file and line location information where the logs were, which is very helpful when you're debugging.
Okay, so not only have we got a lot of stuff in there already, there are also some plans to add some new features into IA. One of the big ones for me is unit testing. So that build, test, and run loop at the moment requires me to compile my program, load my program, and then verify that it's doing something. Now, what we would very much like to do is to be able to actually mock out the BPF program context and accesses into maps so that we can run these, we can write tests and have them run on the host architecture. So we've got a good idea that the business logic of our application is actually working as expected. And then, hopefully then we don't need to compile and load into kernel, which also means that we could have, integration testing or continuous integration rather running for this without requiring root privileges, which should be rather cool. Alessandro? You're muted.
Sorry about that. I just wanted to add that that kind of testing, we actually do it for the user space part already. We mock out syscalls so that we are actually able to test the user space API for maps, for example. That's already there. So yeah, we just need to start doing it for the eBPF side too. So right now we try to be compatible. So for the features that we implement, which are a subset of the features implemented by libBPF, of course, we try to be compatible with libBPF. The way we test that right now is that occasionally I will test on my laptop that I can load programs written in C that target libBPF, that I can load them with AYA. What we're planning to do is to put all this stuff in CI so that we can be reasonably sure that we don't break compatibility too much with libBPF. And then we're going to support more features. Someone is working already on LSM support, and I am planning to work on adding more C group hooks in the next couple of weeks. We already support a bunch of C group hooks, and I'm essentially going to finish the remaining ones in the next couple of weeks.
One of the other things that there's interest in the community is using CraneLift to generate eBPF code. So CraneLift is a code generator, which is currently used for generating WebAssembly, and it is written in Rust. There is also a Rust front end as well, so it can compile Rust code. So it's actually being looked at for compiling debug Rust code because it's quite fast. So one of the things that we're potentially looking at is, could we add an eBPF backend for this? Because we feel that it could open up some interesting use cases. So as it's fairly trivial to add a new front end, we could add a front end for a scripting language to then very quickly spit out eBPF code. And it gives us quite a lot of control over the bytecode, which is generated as well. So it's just something we're potentially looking at. All right, at that point, I think that's the end of our presentation. I hope it's been useful to you, and we'll take some questions.
We got some questions in the chat. Maybe let me read them out for you. So first, Brandon Gregg asks if you're aware of the work that is going on in BCC and BPF Trace to provide binaries without the need to vote LLVM dependency effectively.
Yeah, I've seen. Yeah, I've seen some comments about that, and that is great. That is great for people that do want to keep using BCC or BPF Trace. But the goal of the project is obviously to create a Rust API to also do this. So they're not alternatives, right?
Yeah, that makes sense. Great. And then the other sort of question / clarification is, you said that there's a problem with documentation, and Brandon points out that both BCC and BPF Trace has reference guides, and there's a book that was published by Addison and Weasley. So would you like clarifying the documentation problems?
I would love to clarify. So I guess there are two parts in my mind to documentation. There is the documentation of the technology itself. So what kernel features for eBPF are there? How do they work and how do they get used? And there doesn't appear to be a centralized source for that as far as I can tell. That information is spread everywhere, and it's very hard to try and keep up with that. There is also then the documentation for the specific libraries, and BCC, BPF Trace do a very good job, but they're always going to be lagging behind the kernel features that are available and fighting that as well. So it's difficult. BCC is definitely one of the better examples for sure. I just feel that certainly as a newbie into the space, for me, it was particularly overwhelming. And yes, the book is also very good as well.
All right. The third question we get from Brandon is around well, let me just read it. I'm also curious if you spoke to any of the BPF authors before deciding to rewrite the library. Have you any thoughts on the possible negative impact to collaboration, presumably of not just using the BPF, and how are you keeping up to date with the changes?
Yeah. First of all, maybe it's my fault because I wasn't very clear, but it's not like we rewrote the BPF. Like the API we provide is completely different. There's already a wrapper for libbpf so that you can use it in Rust. And people that do like that do like the libbpf API, obviously can use that, and it works really well, as far as I can tell. But it's as with all APIs, there are bindings to APIs written in other languages. Obviously, some details of the original language leak in the bindings. So obviously, in my opinion, the API could be better. The Rust API, the libbpf Rust API could be better. First of all, the libbpf Rust API seems to be very opinionated. So whoever worked on that API obviously likes that API, and it's completely fine. I personally think that it's possible to create a more idiomatic Rust API. So that was one of the reasons why I started Aya. And also, I'm not sure what you mean by the possible negative impacts to collaboration. The projects are completely independent, and again, it's not like we provide the same API, just a different implementation. It's a completely different API. It's a different developer experience. It's just completely separate.
Yeah,
and as to how to, sorry, just to
ahead.
finish, how to stay up to date with the BPF changes. Yeah, that's really hard. So yeah, that's one of the things we'll have to do for sure.
And just to Alessandro's point about having that idiomatic API, I think that's incredibly important. One of the nice things, especially for me, like I've explained my background as high-level languages and system software, is a lot of the stuff that Rust has for you as a developer is really, really handy. The fact of the really good IDE integration, the fact of built-in static analysis and all of those things. And I would really love to see that expand to encompass eBPF as well. So making sure that we keep those Rust idioms there is really important. I would also like very much, as while I'm developing programs, like Rust does a very good job of stopping me from doing dangerous stuff and avoiding undefined behavior, which is nice. I would very much like to get a static analyzer type tool for the verifier plugged into that code as well. And that's something which would be hard, but not too hard to do for Rust because the tooling and the hooks for that tooling already exist. But I really want those prompts in my editor while I'm writing of, nah, that's not going to pass the verifier. And I think we've got a chance of getting there.
All right, we have one more comment in the chat, but I don't think that's actually a question. So Sergey says that in some ways he feels like the BPF system call itself is sort of an internal BPF API. Let's see if anyone else has any questions, either in the chat or just unmute yourself.
Hello.
All right.
Last question, cheeky last question, sorry. Thank you for your talk. I always wondered what it would be like to generate code for a language that is not coming from a C frontend, not from Clang, and trying to get that to pass the verifier. What has your experience been?
I think this is what is great about Rust, is that, as I said, so if you look at the way we write eBPF code with Rust today, essentially we provide strongly typed APIs for, say, maps. But then once you call those APIs, the code essentially desugars to what you would call from C. So it's essentially exactly the same code. So yeah, it's not very different. And also obviously the LLVM backend is the same. So it's not very different. One thing that is different is the way the Rust compilation model works, because usually when you compile eBPF, when you compile an eBPF program with Clang, you have one compilation unit. Instead, in Rust, you always have multiple compilation units. So that's the only big difference. But otherwise, the code that ends up getting emitted is very similar to what you get with the Clang.
Good day, this is Brendan. I just wanted to clarify one of my earlier comments, and that's about considering the negative impact. Back when I started with BPF, and I think what made BPF observability and tracing work is that we collaborated together on a few main things. In 2014, there were 14 different Linux traces, and everyone wanted there to be one that was finished. And SystemTap, it worked on Red Hat, didn't work on other distros. There were just problems galore. And if you ask me, what was the one thing that we did right? And that was we got people to collaborate and work together on BCC and getting that done, BPF Trace and getting that done. And so it's interesting work that you've done, but I do want to think about where we're coming from it's this collaboration that's allowed us to, I think, for the observability space to be so successful and take the traces as far as we have. We don't want to go back to having 14 different front ends. There can be other front ends, but there really does need to be a strong use case for differentiation. So just to clarify that comment a little bit, I think it's particularly important based on where we're coming from. I fought a lot of those battles to get people to work together so that we didn't have this multitude of tracer problems again. And so I'm hoping we don't go back down that road too much.
That makes sense. I think the part I don't understand is people are going to write eBPF programs with Rust, right? And unless we say that the libBPF Rust API as it is today is the best we can do, we will have to do something else, right? So I think that given the constraint, given the libBPF API, you cannot do that much better than libBPF RS. I think the API looks like that for a reason, right? So I don't think that it's realistic to say, okay, we're going to change libBPF so much that it will be able to accommodate a completely different set of bindings for Rust, right? So I really don't see an alternative to having essentially a different implementation. And it's not only what the API itself looks like, it's also compiling, like Rust as a very solid story for interacting with C code and C libraries. But obviously it involves calling external compilers and linkers and stuff. And that will always have an impact on the experience of developing programs, right?
Yeah, I understand there's a lot of advantages to the Rust libraries. There's going to be shops and environments where people have a Rust ecosystem, they want to add eBPF to that, and it totally makes sense for them. And I don't see a problem with that. You're providing the Rust. I'm a Rust shop and I need to do eBPF. That's what I use. If I'm a Golang shop and I need to use eBPF, I'm going to use the Golang stuff. it's when it comes down to like BPF Trace and BCC. That's where we're trying to collaborate to provide the best high-level language, BPF Trace and BCC for these canned tools. So we can have the core compile once, run everywhere, build these little binaries and run them. And so that's like 3 different use cases I've just mentioned. So you've got, I'm a shop, I'm in a particular language, I need to integrate BPF. If it's Rust, it's this. If it's Golang, it's that, whatever. Then there's the, I want to build some tools, BCC, and then there's BPF Trace for that high level language. So that's, I think they coexist fine that way, but then to start talking about how it's better to write programs in Rust over BPF Trace, that's where I have an issue with. I think BPF Trace is pretty close to pseudocode. Someone might come up with something better than it at some point, but it'll be great to talk about that and explore it. But at the moment, I think that model at the moment is where I see them all fit together. BCC for the tools, BPF Trace for that high level language, and then there's going to be these libraries. It's where there's, you know, where the overlap is, and maybe I'm getting overly worried about it, and that's where I'm thinking about this kind of substituting BPF Trace or BCC when we're trying to collaborate for those particular use cases.
Yeah, I think it might just be, you know, a difference in scale, right? And what you're trying to do. If you're trying to do simple tracing or something which is very well represented inside a DSL, then, you know, BPF Trace and BCC, those things might be the right tool for the job. I think one of the things that drew me to this approach in particular in using Rust was the fact that the problem that I was trying to solve was more complicated than that. It was going to be a lot of code. I wanted to do that inside an ecosystem which I understood, which was Rust. But also one of the really interesting things about the Rust stuff is the crates system. So the fact that we can share code between projects as well and be able to link that in is super valuable. So I've got like some packet passing routines which I've got in a crate, and I can share those between multiple projects, which for me is a massive time saver. So I think as this matures, and also as BPF Trace matures, we'll be able to see that there are definitely differences, I think, which might steer people one way or the other.
Right. So, but do you agree with how I'm trying to fit these together in my head, where we've got BPF Trace as a high-level language, BCC for doing these like canned tools, and then when it comes to the library ecosystems, you can have a Rust thing for the Rust shops and a Golang thing for the Golang shops. Because at some point, I write guidance for beginners, and I need to get my head around this stuff. So if that sounds good.
Yeah, I think the only thing in my mind, right, is that when I started looking at this, the thing that really got me was writing. So BCC is great because it provides you much more context. If you're trying to write a BPF program in raw C, just loading into libbpf or loading with libbpf, understanding that is a much trickier thing. There was a lot of old documentation that was like, you can't use any loops in your C program, and then it was, well, actually no, you can, but those loops have to be bounded, and they have to be bounded in a specific way in order for it to work with the verifier. So, you know, for me, not being familiar with C, that was incredibly daunting, and BCC was certainly less daunting, but still daunting to me. Being able to write programs in Rust for me felt more familiar, and I think that there are going to be some people that just prefer that approach. But I'm not sure where that fits into the 3-layer ecosystem that you provided. You know, either you do it in you write in BPF Trace or your DSL, or you write in C and then have a user space library, or you use BCC through the way. I'm not sure where that would fit, but maybe I'm just I have a strange use cases.
Yeah, I see what you mean. There's going to be some people who they just want to code in Rust no matter what, and they will find a way and they will write those tools. But you know, part of our role as a community is to have guidance to say, if you're a newcomer, this is going to be an easier path for you, unless you for some reason you really want to do that.
Oh no, 100%. Like I mean, just realistically, I don't think it will ever get as easy as using BPF Trace, for example, to start on using BPF. But once you start writing more complex stuff, what Dave was mentioning, like
people keep saying this, but you know, I did write an 800-page book, and I didn't run into an issue once. If I ran into an issue, I went and fixed it, and so the BPF Trace had that capability. And so, in a way, it does map out what I've needed. But if you are running into specific things, please file issues on BPF Trace, and we'll see if they can be fixed. Can't do everything. There is going to be times when you do need something more complicated, but I do push it pretty far.
Oh no, I'm sure, but like one example is I don't know, if you're like what we do at work, for example, like network analysis, it's several hundreds lines of code, and it interacts a lot with user space. Of course, we apply policies and stuff. I don't think realistically we can do that with BPF Trace, right?
I'd have to see the program.
Okay.
I mean, BPF Trace is an observability tool. If you're talking about policies, then you could have entire different algorithms in there. It's something else.
Right. And also at that point, then I guess you'd have to ask, once you have a program that has become, say, several hundred lines of code, do you prefer to write that program with the BPF Trace DSL or with Rust and use the Rust language server, all the tooling? You're going to be able to use the Rust package registry to just link to libraries and stuff like that. I think for complex programs, realistically, you will need something more powerful. And I think that Rust is, in many ways, it's a good language because it's arguably an easy language, and the tooling allows you to do things that you cannot do with BPF Trace today. You cannot do with Clang today. So why?
BPF Trace it's a narrow use case. It's observability.
Yeah.
eBPF does a lot more. So you can just say like, okay, for networking stuff, we can't do it in BPF Trace. We need something else. That's fine.
Oh yeah. So we probably didn't make that clear, but I think that was implied in what we were saying. I don't think we're ever going to suggest people to write a 2 lines eBPF program with Rust, and have to install the compiler and create this package and everything.
All right. There's also a follow-up question from, I think, Daniel, about which parts of the BPF RS API do you think could get most improvement from doing things more idiomatically?
Yeah. Obviously, I am not an expert in BPF RS. I think the fact that it essentially maps almost one-to-one the libBPF API does not look very rusty to me. For example, if you take a look at AYA, if you take a look at how, for example, perf event arrays are implemented, they support async await. They support they implement the Rust traits so that you can, at compile time, make sure that you don't accidentally use things from multiple threads and stuff like that. That kind of thing is, I think, it's one of the reasons why I decided to start AYA.
All right. Daniel, David, do you guys have any comments about the RS part, the Rust part, or should we just call it? No one wants to unmute.
Hi. So I just wanted to add one comment about libBPF RS and not feeling very rusty. The goal with libBPF RS was to reuse the internals of libBPF for all the ELF parsing and to keep the BPF part completely 100% compatible between C, C++, and Rust. if you are filling some, so like what you're talking about, like the trades and the sync stuff, I think that all can be added on top of that. And that was sort of the goal for libpf RS, to provide native Rust abstractions. We're not there yet because we are not big libpf experts, obviously. So we would appreciate collaboration and contributions. Unfortunately, you decided to go like completely re-implementing the internals of libpf. I mean, that's fine. The competition is good, but as Brandon also alluded to, right? Like collaborating and putting all the effort into a single library that would be recommended to users that like want to do Rust development probably would be more productive overall in the long term. But we'll see how it goes.
All right. Thanks for the presentation and the interesting project. I think we should leave it there. So yeah, again, thank you guys.
Thanks, everyone.
We have 5 minutes until the next presentation. So we get the first break. See you guys in 5 minutes. All right, let's do this. Next presentation is by Daniel. It's going to be about precompiled BPF trace programs. Here we go.
Hi, welcome to my talk on ahead of time compiled BPF trace programs. This is a pre-recorded talk, so if there's any questions while I'm giving this talk, hopefully the host can pause the video and then I can answer some of the questions via VC or chat. If not, there will be plenty of time for questions at the end. So before we begin, as a disclaimer, I assume you know what BPF trace is and that you've used BPF trace in some simple use cases. If not, I would encourage you to, pause the video, watch another talk, play with BPF Trace, and then come and watch a recording of this talk later, as it'll probably make a lot more sense. So BPF Trace's current compilation model is totally dynamic. So for example, given this hello world script I have on the screen, once you hit enter, BPF Trace will build the bytecode from scratch, load the bytecode into the kernel. Once the kernel verifies the bytecode, BPF Trace will then attach the progs to the appropriate attach points. So in general, this is pretty okay if you're writing a one-off script, if you're just trying things out. But things get pretty wasteful if you're running the same script on multiple hosts or multiple times. So for example, if you've developed some kind of BPF trace-based tool and you're going to deploy it to 1 million machines, all this work has to be done or redone for every single host. And especially in the case of this hello world script, the output is totally deterministic. The bytecode will never change no matter where you run it. Examples of places where the bytecode might change depending on the host is when you use trace points, because trace points could be added or removed from the kernel. New fields could be added. If you're including any header files, we would need to reprocess these header files every time because the header files don't have to be the same across different hosts and kernel versions. And obviously we'd have to reparse BTF definitions, BPF type format, because the BTF shows you the internal data structures the kernel uses, and these data structures change pretty often depending on which version of the kernel you're on. But by and large, most of the work, like semantic analysis and field analysis, that is the same no matter where you run it. So I bet you're probably wondering now, why is BPF Trace set up to have a dynamic compilation model? Well, for starters, a dynamic compilation model is pretty straightforward to implement. Any information you need from the host, you can pretty trivially access it. For example, if you need to know which kernel functions are available to trace, you can just go open up the file in sysfs and then see what events are available. This is a little trickier to handle if you're doing things ahead of time. Furthermore, things like struct layouts, symbol addresses, trace point fields, if, for example, the user accesses a field in a struct and you compile it ahead of time, now you have to handle the case where what if that field is missing, or what if it's moved? So if you compile things dynamically on the target host, these layouts and these offsets are much more straightforward to handle. You can just assume whatever you find is whatever you find in the BTF or the kernel headers reflects reality. However, to pay for this simplicity of implementation, there's a number of disadvantages to having the dynamic compilation model. The first disadvantage is that shipping and running LLVM on production hosts is pretty expensive in terms of size, memory, and CPU binary size. LLVM is not really known to be lightweight in terms of binary size, memory consumption, or CPU usage. For example, in the past, we've done bad codegen and admitted bad IR intermediate representation to LLVM, and then LLVM all of a sudden goes and uses 1 to 2 gigs of memory to try and compile this bad IR. And this can be pretty bad if you're doing this in production. You can knock over workloads like that pretty easily. Another disadvantage is that time to first trace is slow because we have to run all the analysis. We have to do semantic analysis, we have to do codegen, we have to look at all the fields that people are accessing. We have to pull BTF from the kernel, we have to parse BTF, all that stuff. And then we have to do runtime setup, like create all the maps, load the progs, wait for the kernel to verify, stuff like that. And so we can dramatically reduce the amount of time we can dramatically reduce the time to first trace if we compile scripts ahead of time. And another disadvantage is that it's difficult to sign scripts, especially if you're in security-heavy environments. If you're just shipping a .bt BPF trace script, it's hard to say exactly what the machine is going to run if you're running a compiler in production. For example, imagine if you're shipping .c files to production and compiling it on the fly. Like security people don't really like that too much. To summarize the last two slides, why AOT? Well, the first reason is we can get smaller binary sizes with AOT built scripts. So for example, I just looked on my host and LLVM takes up almost 100 megs of disk space. And to ship that to every production host, that's pretty expensive. And so if we build AOT scripts instead that do not have LLVM built in, hopefully we can save a bunch of disk space on prod hosts plus CPU cycles. Which brings us to the second point. It should be faster to run AOT built scripts as well. The time to first trace will be lowered, and plus we'll stop burning a bunch of cycles on doing duplicated work on all these prod hosts. And the final point is that we can have our cake and eat it as well. So for a long time, there's been a trade-off between BPF Trace and libbpf-based tools, where BPF Trace is easy to develop scripts. You can get something done way faster. But the downside is it's not very efficient, it's kind of slow. So if you actually want to deploy something in production, you have to sit down for a day or two and write a real libbpf-based program. And it takes like a day or two. Even for me, I would say I'm moderately experienced writing libbpf-based tools. It still takes at least one afternoon to write any kind of script. So hopefully with AOT, we can have the best of both worlds. You can have ease of use and ease of development, and then you can ship an efficient version of it to production when you want. So this is the end goal for AOT compiled BPF trace scripts. So in the first line, you can see it's the same hello world script that I had a couple of slides ago, except this time there's a --AOT out.btaot flag appended to the end. And this tells BPF Trace you want to compile an AOT script and you want the output placed in that file name. On the next line, we run file against it and we discover that out.btaot is just a executable file. In the next line, the third line, we run LDD against it and we find out that it's a statically linked executable, meaning that we can just SCP around onto pretty much any Linux host, and in theory it should run all right, which is phenomenal. The fourth line, we run this executable and it runs just like a BPF trace script, except this is fully hermetic and you can just SCP it around, and hopefully it's pretty lightweight as well, lighter, and having a bunch of these is still lighter than shipping LLVM onto production hosts. So this is just the vision. Some of this works, some of it's doesn't fully work yet, and some things I don't have a solution for. There's a bunch of slides later in this presentation about it, so we'll get to all that later, and I'll also show what the current state is. The basic design behind AOT compiled BPF trace scripts is three parts. The first part is we ship a fully executable runtime shim with the BPF trace package. The second part is that when we're compiling the AOT BPF trace script, we're going to first build the metadata, build the bytecode, make a copy of the shim from the package, place that at the user requested location, then take the metadata and bytecode, place that into the special elf section inside the copied shim, thus completing the final executable. The third and final part is that when the shim runs, it knows to look inside itself at that special elf section. It'll then pull out the metadata and bytecode, reconstruct all the data structures, and then begin execution like a regular dynamically compiled BPF trace script would. Hopefully this design seems pretty simple, at least it's pretty simple to me, but as with all things, the devil's really in the details here. There's a lot of details to consider, and I'll go over that later as well. This slide is basically a visual describing more in depth what I was talking about the last slide. There's no real need to stare at this too hard. It's mostly implementation details, like I have a few key functions drawn in the sequence diagram. It's basically saying we're going to add another code path for ALT compile, and that, so if you look at the green highlighted thing, relocate map FDs, and then there's an arrow saying maybe more relocations here too. Basically saying the bytecode that we ship will need to be fixed up before we load into the kernel, because there's things we just simply don't know at compile time. For example, we don't know what the map file descriptors are going to be, so we need to fix that up at runtime. We may need to add more relocations there as well. For example, if we're trying to relocate field offsets or field accesses, and the field might move inside a structure depending on the kernel version, we might need to fix that up as well. So we need to have that step. And then there's another arrow in the middle saying see next slide. We're going to need to add some more passes to the AST passes as well in order to collect all the metadata we need to serialize. This slide is more implementation details. Pretty much what it's saying is we're going to add a couple more AST passes. The first pass we're going to add is to the AOT compiler code path. That's the non-portable feature check, and that exists as a development tool. The reason is I don't want to implement AOT all at once because there's too many things to do. I want to slowly start shipping code gradually with more features over time. And so what this pass does is block features that AOT doesn't support yet. So for example, we're not supporting relocatable struct field accesses off the bat. We're just going to simply disable accessing struct fields if you're trying to compile with AOT. And over time, we'll relax these restrictions. Like there's also other probe types that we're not supporting because I need to think more carefully about how it's going to interact with AOT. Another pass we're going to add is gather runtime resource requirements. That's pretty much another implementation detail. I'll mention it here just in case anyone's curious. For example, say in your BPF Trace script you have a printf and has a format string with a couple parameters and then has a couple arguments to that format string. Well, we're not actually passing the format string itself to the BPF prog because we can't actually do anything with it inside the prog. We can't actually format that format string. Instead, what we're passing to the BPF prog is an ID to an ID that indexes into an array of format strings we store in user space. So when the prog decides to send up a printf, it'll send up the printf ID, and then it'll send up the bytes that make up the arguments for that format string. And then when the runtime receives, this data, it looks up in the array of format strings which format string this, packet of data is for. It looks up what types the arguments are, and then from there it can interpret the bytes that the prog has sent us. And so what this pass does is it collects all these async IDs into this one structure that we can later serialize into the metadata. Before, this used to be all done as part of CodeGen, which was supremely, it was just all mixed in. This just extracts it, makes the logic clear. And then the final pass we're going to add is runtime resource setup. Pretty much all this does at this point is create the map file descriptors. It creates the maps. Previously, this was done in CodeGen, which is not optimal. It's better to just split this out into its own pass. This is the final slide for the implementation details. I promise is the last slide. This one's pretty straightforward. This shows how AOT the shim is going to execute. First extract the metadata, extract bytecode, create the maps, restore the state, and then run. Fairly straightforward. The actual shim file is pretty small. So these are the list of solved problems. And I'll be pretty brief on this because it's not super interesting to talk about the problems I've already solved. The first problem that I solved was, so the map FDs were hard-coded into the bytecode. So originally the maps were being created during semantic analysis and then embedded straight into the bytecode during CodeGen. There's a little too much stuff going on in semantic analysis and CodeGen, so I split that out into a different paths to make things easier to understand. In the process, this solves the problem of the hard-coded FDs because we simply fix up the fake IDs into the real FDs right before loading into the kernel. The second problem was how to handle async IDs. So the async IDs are indexes into an array, and so we still have to make sense of this index when we're running an AOT compiled script. So how do you solve this? Well, the simplest way is to ship all the data with the metadata. So we ship the format string and the args and all that stuff with the metadata structure. Third problem, how do we drop LLVM and libclang dependencies for AOT binaries? Well, I really didn't want to ship LLVM and libclang for the AOT binaries because that kind of defeats the purpose of this entire endeavor. And so the way I solved that was two parts. One, first, new CMake target that creates the AOT runtime target. So this is the shim. So we create a shim, we ship that around with the BPF Trace package. And the second part was I made a change to BCC to make the BCC underscore BPF library essentially the BCC runtime. So everything BCC can do minus Clang and LLVM. And this works great because after you have the bytecode, you don't really need any of that stuff. Note that this is not completely solved, not a completely solved problem, and I might have it in the next couple of slides in the unsolved problems, and I'll talk about that a little bit more. And then the final solved problem was how do I disable the currently unsupported features? You know, the features that I plan on supporting but haven't supported yet. Well, I already talked about that too. New feature check pass on the compile path. Alright, so on to unsolved problems. So for this section of the talk, I welcome any interruptions with people who have ideas, or we can just talk about it after. I'm super interested to hear from anyone who can help me solve these problems. Yeah, without further ado, so how do we create a fully static AOTRT binary? Yeah, well, so CMake, can we finesse CMake enough to accomplish this? Currently the CI, our BPF Trace CI, for every single build on master, we create a fully static BPF Trace binary, and this requires a very specific environment to build. And so I wonder if you can build a non-fully static AOT or BPF Trace binary along with a fully static AOT RT binary. So yeah, I don't know. And then what about BCC? How do we get a fully static BCC going? I think BPF Trace, the CI at least already builds BCC fully static. I'm not sure how it does it, so we have to look into that. And what about libc? Libc doesn't really work super well with fully static builds, so maybe we have to use Moosel or something. I don't know. The next unsolved problem is how do we relocate field accesses on kernel structs? So libbpf compile once run everywhere has already solved this problem, but you have to use libbpf to fix up the bytecode, and libbpf comes with its own framework of how you write and run BPF programs. So yeah, do we use that or do we roll a custom solution? So that begs the second question: is using libbpf for loading feasible? Well, the first issue I have with that is it would require an enormous amount of BPF Trace code changes, because right now we kind of have our own way of doing things. We have our own test frameworks and stuff like that. And so putting libbpf into there is really a non-trivial amount of work. Yeah, like mocking out maps and unit testing, how do you exactly do that with libbpf? Third point I have there is there's a lot of extra overhead, or not. Currently, we do sort of generate ELF files, but not necessarily in the future, because we have plans on creating our own BPF backend to generate bytecode. So we'd have to create an ELF file, and the way you tell libbpf we want to make these maps is you have these magical variables, global variables, in these magical ELF sections saying, oh, this is a map of this type, of this size, with this name, and then libbpf can extract the information and then create the maps for you. And then there's also tension between distro packaging rules and vendoring libbpf, because for libbpf to work the best, we would need to vendor libbpf into BPF Trace, and then we've had pushback in the past about anytime we've tried to vendor anything. Yeah, I'm not too sure on how to deal with relocating field accesses. I'd have to see how complicated rolling custom solution is. So, unsolved, yeah. The next unsolved problem is how do we completely remove LLVM for the AOT binary? So I mentioned a couple slides ago there was one caveat about removing LLVM. So right now the runtime, the BPF Trace runtime, uses LLVM C++ demangler for simple demangling. That's because the C++ provided one does not work very well. There's some issue that I can't quite remember, but it's either too much memory or it was too slow. And the LLVM one is just way better, and I just have no idea how we're going to remove this. Maybe we can go back. Maybe the AOT runtime can use the crappy one, and the the one in the regular BPF trace can use the good one. Yeah, I don't know. So what are we going to do about trace point fields? Are we just going to assume they're stable enough between different hosts and different kernels? Are we going to parse the trace points at runtime for the AOT compiled scripts every time? In my experience, they've been very stable, so I'm curious to hear what the larger, more experienced Linux folks have to say about this. And then the final list of unsolved problems is just kind of a laundry list of stuff I haven't given as much thought about. So first is positional parameters, right? If you're not aware, positional parameters are essentially like a format string. So you write a script with these positional parameters in it, and then when you actually run the script at runtime, you can pass the actual values in the command line, and it'll just fill out the script with the values. So it's like a template. Right now, CodeGen directly places these values into the bytecode or whatever. So unclear how we're going to actually support this. If we need to support it, maybe we could do read-only map or something at runtime. The cur task built-in gives you like the current, the current struct task struct. We need to support field accesses first before we expose that, because otherwise it's mostly useless to access that. So that's not a huge deal. With the field access support, this will be supported. Kadder, uadder, cgroup ID. So this does a lookup during CodeGen, I believe, to find the actual values of find the actual addresses of the symbols. And so obviously on different kernels, the values will be different. So maybe we need to use a read-only map, just like with positional parameters. USDTs, I think the USDTs will be quite complicated to support. I'm really not sure how to do that yet at all. Because you need to look at the binaries that you're targeting for the precise offset and argument information. And I assume this can change pretty frequently, especially if it's not the exact same binary running on different hosts, the exact same trace E. And then watch points, I've given that like no thought at all. I'm just not sure how that would work. Or if it would work at all. Maybe it does work. I just disabled it just to be safe. Because the internals are a little complicated. There's like setup probes and whatever. So after listening to all of my plans and ideas and problems and unsolved problems, you're probably wondering, do you have a prototype? Does it work at all? Where are you at with this? Well, the good news is that I have merged a functional prototype into master. It mostly works, kind of works. However, with a few caveats, things diverged a little bit from my grand plan, but I'll fix them. The first is that the metadata and bytecode currently exist in a separate file, so it's not embedded into the runtime yet. There's no huge blocker for that. I just haven't gotten around to it. It should be really straightforward. It's just a matter of copying over some files around and putting some data in places. So I guess the best example is just one of the tests I have checked into the CI. And this test, you could probably squint along, hopefully can squint along to this. Essentially, we're building a script in AOT mode, placing it into /temp, and then we're taking the runtime and running the compiled stuff. And then it expects a certain output, and it works. Yeah, it works. Any questions?
All right. Daniel, I'll give you a presenter and switch the slides. There you are.
Hello? Awesome, it works. Yeah, so there's a question. Would you get long-term win through porting over to libbpf? Would it be easier to support new features? Maybe. It's unclear. We have all the things we need right now. We don't really use that many fancy libbpf things. Maybe this the BPF linker in the future could be useful if we're using some kind of libraries. But it's a lot of work, and I think it needs to be thought about because the initial work could easily outweigh all of the benefits. And also the vendoring. I think libbpf would have to be vendored in order for it to work the best because it's just such a pain to handle different versions, because right now BPF Trace handles like a huge matrix of features, because we take all these libraries and dependencies as optional, and we'll do different things based on whether or not certain features are present. So that itself presents a huge maintenance cost, and would probably be improved if we could vendor it.
Okay, and do you know what's the status of the alternative BPF backend in BPF Trace? And not the one that is not using LLVM?
So I saw some code come by in like a private repository, and it looks like it was setting up some work. I'm not sure what the status is. I don't, maybe it's paused right now. I think people are kind of busy, because I think all the other BPF Trace maintainers and contributors probably are just volunteers.
Another question. So you mentioned that core is, well, poses some challenges for the AOT. So do you think that the core done by the kernel can help somehow, or dependency on the newest kernel would be too much to bear for the BPF trace?
Yeah, I think it could be done using the new kernel stuff. If we went that direction, I would probably choose to only support the newer kernels, because like individually supporting like user space only stuff and supporting the kernel space stuff, those two pieces are pretty big pieces of work by themselves. So I'd probably have to choose one or the other. Obviously, I think it'd be really nice to support as many hosts as we can, as many users, because there's like a huge long tail out in the wild of kernels. So yeah, I think you added the map indirection thing in the kernel, which is great. So I don't have to fix up the map FDs in user space. But unfortunately, yeah, it only works for like very few people.
You're on mute. Hey, Jacob, I just wanted to say that you are muted. Say it again.
I don't think any audio is coming through. Oh yeah, to support kadder. Yeah, I mean, I think that's what's happening right now with at runtime or during codegen. We're just reading KL sims, or yeah, I believe it's KL sims. Yeah, it's totally doable. It would just be nice to do like as little work as possible on the AOT runtime path. But yeah, that's what we'd probably have to do, and we'd probably put it into some kind of read-only map that the prog is going to read from. just like with the positional parameters, because fixing up the bytecode would be too much. It would be like a little too complicated for like a string to like add a string to the bytecode. So we probably want to do a map or something. Yeah, for a positional parameter, the string would be a constant. I actually don't know how strings work with BPF programs. I would have to look at the details. But I assume like even if you add the string to the section, you would have to fix up the bytecode to read that string. And that just sounds pretty complicated. I'd rather just take an extra indirection with the map lookup. That way everything is unified, like the dynamic compilation, it works the same as the AOT compilation. So we're not like supporting two different things. One is like way less used than the other. Yeah, maybe we could add a helper for the kernel symbol resolution. But then it's like that doesn't fix the user space address resolution though. Maybe that might be too much for a helper. Maybe just better done in user space.
All right, looks like we don't have any more questions. Well, thank you for your talk and all the work that you're doing. That's very much appreciated.
Thank you. Thanks for listening, everyone.
Thanks. We will be back in 17 minutes for the next talk. Thank you. All right, we are back. Next, we have Vladimir talking about DSA. Hey, Vladimir. I gave you the presenter. You should be able to switch slides.
Hi.
Hello. All right, take it away.
How's my audio level?
You sound great.
Okay. So thanks for the introduction. My name is Vladimir Oltan, and I think my camera is not yet started. Give me 1 second. How's that? I work for NXP, the semiconductor company, and I'm here to talk about DSA switches. So DSA stands for Distributed Switch Architecture, and it's a kernel framework for managing Ethernet switches, meaning those multi-port chips that forward packets based on destination MAC address and VLAN ID. For starters, one of the perennial questions coming from driver writers is whether a particular piece of hardware should be driven by a DSA driver or a plain switch dev driver. This might be incorrectly be phrased as DSA versus switch dev, which kind of creates a false dichotomy because DSA and switch dev are not alternative solutions to the same problem. SwitchDev is simply the API that the Linux bridge uses to offload its data structures to compatible hardware, while DSA is a framework. And it has existed before SwitchDev has. And while DSA does now integrate with SwitchDev for the bridging aspects, it also manages many other aspects which are outside of SwitchDev's competence. For example, the defining characteristics of a DSA switch is that when you want to send a packet to it, you never do that directly through an I/O resource that the switch exposes, like a DMA engine or a packet or a register-based MMIO. Instead, DSA switches have one of their ports connected to an Ethernet controller of the Linux host, and to send or receive a packet, you need to do it indirectly through that other driver. So DSA's specialty is kind of managing that relationship between that host port called DSA master and the switch itself. To get you in the right mentality for understanding DSA's goals, it's important to mention that while all of the ports of a DSA switch might be identical from a hardware point of view, the framework treats them differently according to their role. That port I was mentioning, which connects to the DSA master, is called the CPU port. It's, if you will, an infrastructure port, and it's a shared port, which is only used to pass packets back and forth to other ports. So to the network stack, it really serves no purpose, and user space doesn't need to know about its existence. The other ports in the picture labeled switch ports 0 to 3 are front-facing ports of the switch, and they are called user ports in DSA terminology. A user port has a network interface associated with it, and that interface is expected to be capable of receiving and sending packets through it. But the transmit and receive functions for the DSA network interfaces are kind of strange, and they look much more similar to the data path of a virtual interface like a VLAN than those of a normal hardware driver. So this is because DSA switches typically have the ability to insert tags in the packets when they send those towards the host. And similarly, they understand the metadata tags that are placed by software in packets when the software sends them one, and they will interpret those tags and then strip them when they send the packet out. One more thing, generally speaking, DSA switches can be connected by board makers to any Ethernet controller, and therefore, one of the DSA's design goals is to permit any unmodified Ethernet driver to behave well as a DSA master. For reception, DSA uses a packet type handler, which parses the tag added by the switch, it strips it, and then redirects the SKB towards the virtual interface, which corresponds to the user port that the packet has ingressed on. So those were the user ports. Lastly, there is a third class of DSA port roles, which are not shown in this picture. And these have to do with the D in DSA, and D stands for distributed. And that's a totally optional feature, which means that switches can have cascade ports towards other switches on the same board, and they can build really complex and diverse topologies. These cascade ports are simply called DSA ports, for lack of a better term, and similar to CPU ports, they are shared but are irrelevant to user space. So only the user ports are. So DSA doesn't create any network interface for cascade ports either. They are hidden and configured implicitly. So you're a user, and when you use a board with several DSA user ports and they belong to different switches, that's pretty much invisible to you, and you don't need to do any special configuration at all. DSA just manages the entire group of switches as just one big switch tree, the switching fabric. And it brings the shared ports up automatically, and the DSA master, again, it brings it up automatically as well. So all you need to do is just open the user port, put an IP on it, and then start using it. Okay. So again, as part of user experience, there isn't any user space tooling that's specific to DSA, quite the opposite. And DSA ports don't even switch between themselves by default, and that confuses some people. If you want to enable switching between two ports, what you can do is just create a Linux bridge and put the network interfaces of those ports between it, under it. And you can also create a second bridge and put other two DSA ports under that second bridge, and you've just created a second forwarding domain, which is isolated from the first. By the way, if you have questions, I might not pay full attention to the chat right now, but there are logical pause points between slides, and that would be a good moment to do so verbally.
Hey, Vladimir, Saravana here. Good to see you in person.
Hi.
We had a question on the previous slide, just to kind of understand the DSA architecture. Is the intent of the architecture or framework to kind of just make it appear to user space as if each of those switch ports or SWP, as if they're just part of the host device? Like, is that the abstraction you're trying to achieve?
The abstraction is that the only thing they expose to user space are network interfaces, and
right.
Those interfaces are just like any other user interface.
Right. So to them, they're no different from ETH0. They're like, you can't hide the fact that there's a switch underneath. Okay.
Exactly.
Cool. Thank you.
Okay. Thanks for the question. Nice to hear you, by the way. Okay. So if you've been following the first part and you've been thinking, wait a minute, did you just describe an Ethernet port multiplexer with in-band channel selection? You know, my switch is really not like that, like at all. Yep, that's what I did. So that's also the main talking point of my presentation and the reason for the title, Domesticating a Savage Beast. The networking maintainers, typically when they see a driver posted for an Ethernet connected switch, they say, oh, you need DSA in your life. And now, having recently joined that club, I kind of see where they're coming from. But I'm also here to tell you that, okay, it's not so bad. Let's just discuss the changes that we've been making to DSA in the past few years in order to not shoehorn that model on top of switches that really are thought out differently. So please consider that if there really was another way, like setting up the switch in the bootloader and then never touching it again, or writing a user space driver for it, but then leaving file management up in the air or whatnot, if any of that would have worked just fine, I would have not been here talking about DSA. And I am going to go through these individual things in the next slides. So one of the greatest ways in which switch implementations vary from one vendor to another is their view of the management model. So the majority of network switches which are capable of management, have some sort of distinction between the data plane packets and the control packets. These different flows are superimposed on top of the same hardware ports, and that's important to understand. So to visualize that, it may be helpful to look at them three-dimensionally to see the key differences between these two planes. So at the most basic level, control packets must be used for link layer control protocols like STP and PDP. And that's because they have the ability to target a specific egress port and to override its STP state. That means to inject into a blocking port. These control packets, they are made to typically bypass the forwarding layer of the switch and the frame analysis stage of the CPU port as well, and are injected directly into the egress port. And one of the implications of that, at least the one that's really relevant here, is that hardware address learning is not going to be performed on the CPU port for this type of packets. And generally speaking, you could see the CPU port as essentially a God mode port for control packets. There's the opposite side of the spectrum as well, and those are the data plane packets, which don't perform STP state override. They are subject to hardware address learning for the CPU on the CPU port, but they also cannot be steered towards a precise destination port, since they are, of course, subject to the forwarding rules of the switch. And the format of these packets, again, might vary wildly from one switch implementation to another, but it can vary from a special bit in the DSA tag, which says, okay, I am a data plane packet, to the complete absence of a DSA tag. So for these packets, the CPU port essentially acts as any other bridge port. Okay, so now a bit of classification. Depending on the volume of control packets that get sent back and forth between the host and the switch, I like to think of there being like three different classes of switches. On one hand, I would like to call fully managed those switches where all traffic can be sent as control packets towards the switch, and that is an operation which can actually be sustained at line rate. DSA's assumption, unfortunately, has been that this will be the case for all switches. So for the longest time, the DSA tagging protocols have all constructed only control packets. There is one special case of devices, however, that seem to not support control packets at all. And for those, DSA has used a no-op tagging protocol. And this behaves radically differently from all the others, because the interface for the user ports are essentially dead in terms of packet I/O. So they are only registered for interacting with the file library, but otherwise a user's gotta send traffic through the DSA master and the switch just switches. So this is really the opposite of the model that DSA is kind of trying to enforce, and it really hurts it overall, because we do support it in tree for a couple of switch drivers, and to some people that usage model is the only one they've seen and the only one they know. Okay, so what do these people do when they want to send a packet towards a precise switch port, when the only thing they can do is send through the DSA master? Well, they create a bridge. They set up a bridge VLAN that includes only the desired egress switch port, and then they create a VLAN upper interface for the DSA master, and then they send their traffic through that VLAN interface. Okay, so now I'd like to move on to the third category, and I'd like to call this lightly managed switches and focus on it just a bit. For the lightly managed switches, control packets are supposed to be used for just that. Link local control protocols, so nothing more. Sending a control packet may be an expensive operation, and it may not be able to be sustained at line rate. So as far as the hardware design is concerned for these, the bulk of the traffic, meaning the data plane packets, should be injected with no DSA tag at all, or otherwise said, directly through the bare DSA master, basically just like in the case of unmanaged switches. Yeah, but having control packets transmitted through one net device and data packets through another is even stranger than just sending them all through the DSA master. So something needs to be done in order for data packets to be sent through the switch virtual interfaces, and that's one of the changes that were made. This a while ago. This is the reason that has led to the introduction of the software-defined DSA tagging protocol, which is called Tag 802.1q. And this basically does the same thing as what is being done with the unmanaged switches with the no-op tagger, and that is to steer packets towards a precise switch port using VLANs. But the difference is that with Tag 802.1q, we do this in kernel. So basically, it just looks like any other tagging protocol, and you preserve the DSA usage model. You absolutely still don't need to use the DSA master for anything. You could keep ignoring it, and that's the whole point. The way Tag 802.1 works is that source port identification on RX relies on the hardware inserting a certain port-based VLAN ID that uniquely identifies that port. The problem is that this only works when the port is standalone or under a VLAN unaware bridge. When the port is under a VLAN aware bridge, the packet might have a VLAN ID which is not port-based, and needless to say, not unique to that port. So kind of there goes the source port identification based on that. So yeah, Tag 802.1 can push us further, but not far enough. VLAN-aware bridges are indeed an important use case, and we should have a lightweight solution for supporting CPU-terminated traffic, even in that case. Okay, so at this point, just take a step back and just go back to the hardware designer and just ask them what to do, and they'll be confused and ask, so why do you need to know which source port this packet came from exactly? It came from the bridge. And while that does make you pause for a bit, there is some truth to it. So let's try to implement it and see how far that gets us. We don't know the precise source port, so just lie and report a plausible one or imprecise. Okay, so as long as you satisfy some basic sanity requirements inside the software bridge's ingress path, then it turns out the bridge is happy to accept that packet as valid. And it's even going to process it on behalf of the imprecise DSA port that was reported. So, okay, we've solved reception, but that breaks transmission. And the complications come from the fact that the software bridge might learn the source MAC address for these packets on a potentially wrong port. And then on the return path of those packets, they are the bridge is going to deliver them towards that wrong port. So we need to kind of insert another hook. We need to give DSA the chance to right the wrong and fix a lie. And that chance is actually called the TX forwarding offload, and it's a brand new bridge feature. So it goes like this. The software bridge avoids cloning an SKB, which needs to be flooded to multiple ports, and it sends only one copy of the packet towards a single network interface from each hardware domain, quote unquote. And this is a new concept as well. It's I'm going to explain that further. From each hardware domain that the flooded packet must reach. So then it becomes the responsibility of the port driver to look up its own hardware FDB for this packet and replicate it as needed in hardware. So this is a feature that's of course useful in itself, and is one of the reasons it got accepted. And it was in fact initially submitted by Tobias Valdekrans for an entirely different purpose. Because with switches which have a large port count, you can significantly reduce the amount of multicast traffic that you send on that link between the DSA master and the CPU port, because you replicate the packets inside the switch and not with SKB clone. And in the general sense, for hardware that declares the TX forwarding offload feature, the bridge basically partially lets go of its FDB lookup and delivers the packet with SKB offload forwarding mark set to true, which means it's a data plane packet. Okay, so how does that help us? How can the lightly managed and unmanaged switches send data plane packets? Well, at the very least, they can insert no DSA tag at all and just let the packet slide into the hardware, basically not telling the switch what to do with it. It's basically an I'm feeling lucky packet. So just this time, it's not sending it through the DSA master, it's sending it from the DSA network interface. So this works, and it also makes the imprecise reception work correctly because the transmission is also imprecise. So to explain that, even though the software bridge learned the MAC address on the wrong port, that source port is in fact in the same hardware domain with the right port. And even though the software bridge is the FDB of the software bridge is incorrect, the hardware FDB isn't. Okay, that was this slide. 10 seconds of pause. If there isn't any question, I'm going to the next one. Okay. Next topic is offloading and on-offloading upper interfaces. So recently, DSA has gained support for offloading other virtual network interfaces than the Linux bridge. And these are the HSR driver, and this supports the HSR and PRP redundancy, industrial redundancy protocols, and the bonding and team driver, which support the link aggregation protocol. Sadly, I'm not going to go into details on these because they're not the main topic, but this work has triggered a discussion. Well, not all switches are capable of offloading HSR and lag, and DSA's policy has always been to fall back to a software implementation, since the bandwidth to the CPU is oftentimes not that bad that this is impractical. So maybe we should do that. Okay, but it turns out we can't really enforce DSA's policy right away with the expected results, at least, due to two major roadblocks that we faced. And first is the Linux bridge, which through switchdev makes a wrong assumption about ports being capable of offloading forwarding, because it bases that decision on the physical switch ID, which is reported by the bridge port net device. In that case, it's the bonding interface. And the physical switch ID is actually a recursive call that goes all the way down into DSA. But of course, from DSA's perspective, to not offload an upper interface, it means that the physical port should behave exactly as it would if it was standalone with no switching. So the physical switch ID was the metric based on which switchdev determined whether forwarding between two net devices would take place in software or in hardware. And that means same switch ID hardware, different switch ID software. But there were two different interpretations of the same configuration. And this has led to a redesign of the switchdev API, in that drivers must now explicitly mark themselves to the bridge the network interfaces that are capable of autonomous forwarding. The new default, of course, being that they aren't. So in this new model, even if two interfaces report the same physical switch ID, they might yet not be part of the same hardware domain for autonomous forwarding as far as the bridge is concerned, and forwarding between them should take place in software. That was issue number one that was actually solved. The second one, which is still in progress, is FDB isolation in switches. So up until this point, the vast majority of DSA drivers, as well as the framework itself, have considered that it's enough to offload multiple bridges by enforcing a separation between the ports of one bridge and the ports of another, just at the forwarding matrix level. Meaning port A can forward to port B, but not to port C. So this works as long as the same MAC address, or in the case of VLAN where bridges, MAC plus VLAN pair, is not present in more than one bridging domain at the same time. But the issue, which is described in the picture, is that a DSA switch is still a switch, surprise. And for every packet that it forwards, regardless of the configuration of this ingress port, it will attempt to look up the FDB to find the destination. So in the picture, when the packet is received on the standalone switch port 0, which is under an unoffloaded lag, it will see the FDB entry pointing towards switch port 3 from the hardware bridge, and then it's going to try to short circuit the CPU and forward directly to switch port 3, but due to the isolation rules we have at the forwarding layer, that is blocked, so it will fail and it will drop the packet. So what's FDB isolation? It's this hardware-specific mechanism which we're going to put in place to prevent that in individual drivers, and it makes FTP lookups performed on a source port stop matching FDB entries that point towards a port that is not in the same hardware forwarding domain. And there are going to be API changes that encourage drivers to do this and associate FDB entries with a given bridge ID and not have them visible in the global namespace. Okay, another 10-second pause. Okay, next topic, RX filtering, and in the context of DSA, RX filtering refers to the technique of teaching switches which addresses must be filtered towards the host and delivered to the CPU ports. So even if no such thing as a MAC address for a switch port exists, because it forwards, never terminates, DSA network interfaces do have one since they are capable of more than forwarding. That's kind of the premise of the model. And by default, that address is inherited from the DSA master, but there's an option to override the address of each port from other sources like the device tree. And traditionally, DSA has not configured the switches in any way so as to make sure that packets which are destined towards the switch ports addresses or the DSA master's address or bridge upper interface address are filtered only towards the host. So what's going to happen will, of course, depend on exactly how the hardware works, but the typical case is that of a switch where software is going to send only control packets to the hardware, and the switch is, of course, not going to learn from these packets, so it will never be aware of those addresses, or maybe it flat out can't learn the addresses. So in that case, any rule matching these packets is simply absent from hardware. So the packets destined for the host are going to reach it via flooding. The packets, however, are not going to be flooded only to the host. They're going to be flooded towards all other ports that are in the same bridging domain as the ingress port. So yeah, needless to say, there was a desire to address this. But that wasn't the only problem. It turns out that addresses corresponding to host interfaces aren't the only ones that need to be sent to the CPU, not via flooding, because there are many kinds of use cases where DSA switch ports are in a bridging domain with so-called foreign interfaces or non-DSA interfaces. And the typical example of this is a Wi-Fi router where the LAN ports are handled by a switch, and that switch is in the same bridging domain with a Wi-Fi access point. In that particular setup, the effects of not having address learning on the CPU port can be much more disastrous. For instance, when there are migrating stations from the LAN ports towards the Wi-Fi access point, which is behind the CPU port from the switch's perspective. So not going into too much detail, you'll effectively end up with a stale address, which is going to cause packet loss until it expires. And there was also a desire to fix that second issue. So, okay, but where to fix these problems? Another thing I need to point out is that if we take into consideration that FDB isolation thing discussed earlier, standalone ports do not have a problem here. And this is because Standalone ports should be placed by drivers in a hardware FDB partition where no learning takes place and packets are flooded only towards their only possible destination, which is the CPU port. Okay, so the issue needs to be fixed at the switch dev level, and just like that, DSA became a lot tighter integrated with the software FDB of the bridge, and it started sniffing for two classes of FDB entries and offloading them as FDB entries pointing towards the switch's CPU port. Class 1 are FDB entries which are learned on foreign interfaces in the same bridging domain as a DSA switch interface, and this solves the Wi-Fi roaming issue by introducing an opt-in feature which is called assisted learning on the CPU port, and this actually replaces the hardware alternative which may be missing. And second class of FDB entries are those that are local or permanent, and this actually means the same thing, which is not forwarded. So the bridge marks the MAC address of each bridge port as a local address, and the same goes for the bridge's own MAC address. And by offloading these entries to hardware, packets targeted towards the bridge itself are no longer flooded in the entire bridging domain. Ooh. Okay. If there are no questions, let's go on to something a bit more lightweight, which is to talk about DSA support for cross-chip bridging, aka the DNDSA. So traditionally, the cross-chip setups supported by DSA have been daisy chains. And the definition is that all switches except the topmost one lack a dedicated CPU port and are simply cascaded towards an upstream switch. And cross-chip bridging refers to the ability of packets that are ingressed on the port of one switch to egress the port of another switch without going through the CPU. So it's important to mention that DSA declares that all switches belonging to the same tree have the same physical switch ID from switch dev perspective, which makes the bridge treat them as a single switching fabric. So daisy chains worked just fine, but I've had the pleasure of learning about two completely new switch topologies, and these needed some work and brain power, and I'd like to discuss them even if very briefly. So one of the topologies we've had to support is a board with multiple switches that don't understand each other's DSA tags, but were nonetheless connected together. So a DSA tree is by definition comprised of all switches which are connected directly to one another, and they use a compatible tagging protocol. This was not the case here, so the correct paradigm is for each switch to constitute its own switch tree with one element, hence the name, disjoint trees. In this picture, there are 3 trees, there's one internal switch, and connected through SPI are 2 external switches, one hanging off of each of the first 2 internal switch ports. So the ports of the internal switch are both user ports as well as DSA masters, but what they are not is DSA or cascade ports. Okay, so for this topology, there were 2 distinct questions to answer. First, for traffic termination, would tag stacking work well? And the second question for autonomous forwarding, who would make sure that the tags pushed by the ingress side of switches are popped in all cases by the egress side? So the first question was kind of easy to answer because a packet received by switch 0 port 0 will end up having 2 tags on the topmost DSA master, which is ENO2. The tags are, of course, going to be stripped in the order determined by the switch's proximity to the topmost DSA master. And since the directly attached is to ENO2, which is topmost, is the internal switch, that's the tag that gets stripping first. The new owner becomes switch port 0, and so on recursively. Okay, the other question, what happens when a packet is forwarded from its external switch 1 to 2? So that's way more interesting in my opinion, and something that was not supported before. So the joint trees were supported already, but if you want to enable forwarding between switch 1 and 2. Like, for example, you create a BR0 interface and you put all of switch 0 port 0 to 3 and switch 1 port 0 to 3 into BR0. That's how you tell the system that you want cross-chip forwarding. So we've modified the DSA API to permit cross-chip bridging between these between ports belonging to any tree. But even then, we need to establish some sort of ground rules. So for a packet to be forwarded between these two switches, it must go through the CPU port, and in the most basic configuration, that happens in software just fine. But of course, we would like to accelerate that because, you know, the internal switch is a switch, and it's desirable that it doesn't hit the actual CPU. And as long as the internal switch has some elementary understanding of the packets, even after they've been mangled by the external switch's DSA tag, that should in fact still be possible. And what you need to do in that case is you create a second bridge BR1 and put switch port 0 and switch port 1, which are the DSA masters, in BR1, and forwarding happens 100% in hardware for these. I see we're kind of running a little bit late, unfortunately. I wanted to talk about H trees a little bit, and maybe I'm just going to say what they are. And it's actually a name invented by me, so drop me a line if you have a better suggestion. The name comes from the fact that there are multiple switches which are laterally interconnected through cascade ports, but to reach the CPU, each switch has its own dedicated CPU port. So that differs from daisy chains. And it turns out that to support such a system, there are two distinct issues. First is with regard to RX filtering, you need to avoid addresses bouncing between the CPU port of one switch and the other. And the second issue has to do with packet loops, because it's actually possible to send the packet towards one switch, that switch to send it to the second switch, and the second switch will flood it towards all ports, including to its own CPU port, where this packet will be again processed as a receive packet. Okay. So the wrapping up slide, and I'm sorry that this is so late, is that we've been extending DSA in two directions, and this took a good amount of creativity more than anything else. And the first direction is in breadth. We tried to cover a wider variety of switches and try to have better means from now on to cover even more, and also support new switch topologies that these switches come in. And we would like to have more open discussions with vendors that have their special view of the world, and see what we can do to make DSA a better framework for that. And the other direction is in depth, and we have fixed some long-standing issues, like, for example, the lack of RX filtering. And there's still a lot to go. And if you are interested, you could go check out the full paper. So that's about all that I had to say. So thanks.
Thank you. We can take a question, I think maybe one or two, if anyone has any questions.
Andrew Lunn says, the switch dev model is that each switch port looks like a normal interface. DSA provides a framework to make this happen, but pure switch dev drivers also do it. Yes, this is a correct point. So it is basically the responsibility of switch dev that we have a network interface for each port. But on the other hand, device manufacturers that make discrete switches will never end up complaining about switch dev, because they're not going to write a pure switch dev driver for them. So DSA kind of gets all the blame for that. But of course, you're right. It's the switch dev model to blame. Although, on the other hand, to be fair, DSA has enforced the same model even before switch dev, so maybe that's something to think of.
We kind of out of time, but I'm kind of curious, what do you think about testing? Because it seems like there's a lot of divergence between the vendors, how they behave and how they interpret things. And I would be really scared that when I'm changing something, I will break someone's weird application running on a 2-year-old kernel, and then I will not know for another 2 years.
Yep, that's kind of the biggest problem. So one of the things we've been trying to do was try and compartmentalize, I'm not sure what the word is, basically create clear categories, like for example, for tagging protocols, this is a big thing. We have distinguished between taggers that put their header before Ethernet, at the place of the ether type, or at the tail of the packet. And we have some sort of testing support for tagging protocols to be run on a generic interface. Basically, that's the DSA loop. And the maintainers actually do that from time to time when they see a new tagging protocol being submitted to the kernel. They test it on what they have, even if they don't have the hardware. But of course, there are a lot of things that you can't cover. And what we try to do is simply ask questions to understand what is kind of the mentality between the behind that particular hardware model. I don't really think we could do a lot better than that. We have some testing for the data path, but the switch control path belongs just, you need the switch.
We tend to have a lot of community support here. It's a very active subsystem, so people tell us when we break it, and we fix it quite quickly.
Yeah, that happens too.
All right. Sounds good. I remember when I was working on BPF offload, the BPF offload would break from time to time because people were changing BPF. So I thought it was better to just add tests and try to, as much as possible, at least provide some abstract tests. So they can be run by a CI effectively. But I mean, you probably have to run tests on your own hardware whenever people post patches, right?
We don't yet have like a consolidated self-test infrastructure for DSA switches. There are some patches, there have been some attempts to do that. There's nothing in mainline yet, but maybe we could do something about it.
Some of the self-tests that Mellanox provides kind of work might do, but they tend to assume lots of ports, and we tend to only have a few ports, so that's a big problem.
Yeah. Anyway, for the FDB isolation path series that was posted a few weeks ago, there was a self-test associated with that. Like, let's say I was removing the RTNL mutex from FDB add, and that might have turned up some race conditions in the driver. I did catch some of those in the drivers I maintain with a self-test. I did provide them as part of the past series. Of course, that isn't merged yet, but maybe there's a start for anything, and things like FDB dump nonstop. While you add an FDB entry, that could be also nonstop, that could be a starter. Also, things that are not always geared towards the same stuff that Mellanox is trying to do with their hardware, because I'm feeling that we're targeting very different spaces here.
All right, since we're out of time, let's cut it off here. Thanks a lot for the talk and the paper associated, a lot of great info in it as well.
Thanks a lot for listening.
Thank you. So that concludes the presentations we had for the day. Thanks a lot for everybody for attending and asking questions, and for the talks that were presented. See you everybody tomorrow. Bye.